point of this first module is to talk about, well, really four things. First thing is we want to talk about Go, why it's good, why it's unique, right? We want to motivate you, just tell you why do you need to even learn this in the first place as compared to existing languages, because there are many, right? So we'll talk about that. Then we'll have you start using Go. So this specifically means installing the Go environment and compiling your first program. You need to get through that before you can go on with the rest of the course. So we'll sort of walk you through the installation process and show you how to just compile a program and see that it works as a sanity check for the whole setup. Then we'll start talking about the code organization, the recommended code organization. So workspace, so how you define your workspace, how it should be organized, how Go code is organized into packages to allow you to share. So a big point of Go is sharing with other people, right? Because if you think about any real software you write, it's always big, right? You work with other people. It's almost never just you alone. And so you got to share, and packages help to make that easy and to organize the code so you can trade your code with other people. Then at the end of this module, we'll start talking about variables. Start talking about the language itself. So the variables, what types there are, and how do you do scoping, how variable scoping happens. How you can determine, how you basically resolve the value of a variable depending on where it occurs and where it's defined. So why should you learn Go? What's unique and good about the Go language? I'll go over some of the highlights of that. Different people have different opinions, but there are certain features that are pretty uniformly understood as being advantages of the Go language. So some of the advantages of Go. First, runs fast. Okay, that's always a good thing. And I'll talk a little bit more detail in these slides about why it runs fast. And faster than what, right? It doesn't run fast in everything, but it runs fast in a lot of things, and we'll talk about why. Garbage collection, that's another feature that in similar languages, meaning languages that run fast like Go does, they don't have garbage collection. So garbage collection is a really useful feature. I'll describe what that is. Simpler objects. Now this could be an advantage, a disadvantage, but the idea is that Go is essentially object-oriented, although some might disagree, but it has this concept of objects. And these objects are generally, the object orientation is a little simplified as compared to other languages. So this is good. It makes it easier to code. You don't have to use these complicated features. Of course, you never had to use them anyway, but it makes it faster and simpler to use. So now somebody might argue that, look, these features are useful features. I wanted them. Okay, but Go is actually a simpler object-oriented implementation than you would see in other languages like, say, C++. And another feature of Go is that it has concurrency, efficient concurrency implementation built into the language. So there are a lot of these concurrency primitives that are built into the language and that are efficiently implemented, and we'll talk about those. So to start off with, let's go into that code running fast thing and tell you why that is the case. And to talk about that, we've got to talk about a little bit about languages in general, differences between languages. So I've got these three very broad categories of languages for machines. So one is machine language, next is assembly language, next is high-level language, right? Now that's a really big category, but let me explain. Machine language, you start off with, that is the lowest level language, and it's directly executed on the CPU, on the processor. So the machine language instructions are very, very straightforward and simple. Add, multiply, add might add to register contents, put the result in another register, something like that. Very small steps, each machine language instruction. Now, and this runs directly on the processor. So there's that. There's assembly language, and assembly language is basically machine language, almost a one-to-one mapping to machine language. So in machine language, say you had an add instruction, that might be represented as a sequence of zeros and ones, 1, 1, 1, 1, 0, 0, 0, 0. That might be an add, opcode for an add. So in assembly language, you would use the word ADD, right? So it maps one-to-one to the machine language equivalent, but you can read it because it's English. Now it's concise English, and I would argue it's hard to read, but it's English mnemonic, so a human could read that and could write that if you wanted to. And people do sometimes. If you want something to run really, really fast and really efficiently, then you'll write it directly in assembly language. you know, that's outside of the scope of this class. That's hardcore, I would call it. That is not something we're going to really cover in this class, but sometimes you do write directly in assembly language. So there's assembly, machine and assembly, and assembly language is basically a one-to-one mapping to machine language. Not completely, but very close. So fundamentally, they're the same complexity. They're the same language, but assembly language is easier to read. Now, high-level languages, that's everything else, okay? That's a broad category. A high-level language is a language that essentially humans commonly use to program in. They are much easier to use than assembly language or machine language. They provide you with lots of abstractions that any programmer would be used to. For instance, variables, right? Assembly language and machine language do not have variables. They have memory, and you can put stuff in it, take stuff out, right? And there's no idea of a type or anything like that in assembly language, machine language. But high-level languages provide that to you, right? If statements. Now, assembly language, machine language, they have conditional branches and so on, but these are generally much harder to use than your standard if statement that you would see in any normal high-level language, or loops, or for loops, things like this. You can create these things in assembly and machine language, but they are harder to write than they would be in a high-level language. So high-level languages are basically everything that most people program in. So one thing, so you can imagine these different categories. Now, the languages that we're talking about, Go is, of course, a high-level language. In this set of lists, in these three categories, it would be considered high-level. Remember that term high-level is subjective, okay? But I'll call it high-level. So all software, what I have highlighted in the slide, all software needs to be translated into the machine language of the processor to be executed. So what that means is that if you've got a processor of some kind, some i7 or whatever processor you're working with, that processor does not know C or Java or Python or Go or C++ or any of those, right? All it knows is its own machine language, say x86 machine language if it's an Intel-based processor, right? Or an AMD or something like that. So it knows that machine language. So in order for the code to execute on the processor, it has to be first translated into the machine language of the processor. So even if it's C, Python, Java, whatever it is, has to be translated. So there is this software translation step that has to go on. Okay, now this translation step, it can go on in one of roughly two ways. It can be compiled, there can be a compilation or interpretation. Okay. Now, a compiled language is a language where the translation from the high-level language to the machine code happens one time before you execute the code, before you deploy the code. It happens one time, okay? So like in C, C++, Go, Java partially, there's a compiler. And you compile the code. So somebody writes the source code, they compile it, and then they execute it. And they execute the compiled executable, right? The compiled executable is basically machine language code, plus other stuff, but it's basically machine language code. So the idea behind a compiled language is, the key thing we want to bring out anyway, is the fact that this translation occurs once. It doesn't occur while you're running the code, right? It happens before you run the code. And then when you run the code, you are just running the machine language instructions directly because they're already compiled into machine language by the compiler. So the other way to do this is interpretation. In interpreted language, what happens is instructions are translated while the code is executed. So if you got so what happens is it adds time to the execution, right? Because every time you see an instruction in, say, Python, that instruction has to be translated into machine code on the fly. And that takes a certain amount of time just to do that translation. So in addition to actually executing the instruction, you've got to do the translation from the instruction into the equivalent machine code. So that slows you down. So the translation occurs every time you run the Python code, say, or Java, right? The Java bytecode. I put Java as partially in both categories because Java has, it's compiled, but it generates what's called bytecode, not actual machine code. And then the bytecode has to be interpreted at runtime. So there's an interpreter also, the Java virtual machine. But these interpreted languages require an interpreter to be executing while you're running your code because it has to be doing this translation as you execute the code. And so that slows you down. Now, there's this trade-off between compiled code and interpreted code. The first level of this trade-off, one big difference you can see is that compiled code is generally faster to execute. That's because you don't have to do the translation every time you run the code. So it's going to be faster. Now, there are people who would argue the opposite, but generally compiled code is a lot faster. Now, on the other hand, though, interpreters make coding easier. So the thing about interpreters is that the interpreter itself, that program that is doing the translation of your code, it can help you. It can handle things that you as a programmer don't want to handle. For instance, in Python, I don't have to declare my variable types. I can just start using a variable, and the interpreter will say, it looks like he's using it as an integer, make it an integer, right? So that's something that the programmer doesn't have to think about. Another thing that interpreters commonly often have, is memory management. In fact, almost always they have this. They can manage their memory, and by that I mean getting rid of variables and other pieces of data when you're not using them. So when you use a variable, that variable has to go into memory somewhere. And that memory, if you keep making variables and using up memory space, you will eventually run out of memory. Things will slow down, you'll run out of memory. So you have to manage your memory. That is, when you're done using an object, you want to get rid of that, deallocate it from memory. And that happens automatically in an interpreted language. So the interpreter handles that. So that's a good thing about interpreters. So Go is a good compromise between this compiled and interpreted type of language. It's a compiled language, but it has some of the features, some of the good features of interpreted language. Specifically, it has garbage collection. So garbage collection is the automatic memory management that I'm talking about. So this memory management, where should memory be allocated? So I say, I need a variable X. Where should it put it in memory? What type of memory should it put it in? We'll talk about that a little bit later. But also, when am I done with that memory, right? Because when you're done with the memory, you can get rid of the memory. You don't have to use it anymore. You can use it for something else. So that's what I talk about memory management. That's what I mean. And this happens automatically. The garbage collector can figure that out. It says, it looks like this program is done with variable X. I will free that memory now. And that happens automatically. Manual memory management is hard, okay? And, this is, if you've ever done C or something like this, you know this. Deallocate memory too early. If you stop using it too early, then you'll have false memory accesses because you still need it. So you'll use the memory that's already deallocated, and errors crop up because of that. Also, if you deallocate it too late, then you're wasting memory. You can have what's called a memory leak, where you have more and more memory that's not actually being used, but it's being blocked up because your machine thinks it's being used, right? So memory management manually is very difficult, and there are lots of errors, security errors too. So Go has a garbage collection package included, garbage collection code included. So when it compiles your code, it also compiles garbage collection into your code automatically. And this is typically only done by interpreters. So this is a compiled language that actually has garbage collection, which is a really good feature. Now, downside is that it slows down the execution a bit, but it's an efficient garbage collector, so it doesn't slow it down much, and you get a lot of advantage out of having this automatic garbage collection. So Go language is object-oriented, but let's say weakly object-oriented. So what I mean by that is that it implements objects, but maybe they have fewer features than you would see in another object-oriented language like Python or Java or C++, something like that. So we're going to go through, I'm just going to summarize what object-oriented languages are, what object-oriented programming is, very briefly, just so I can highlight some of the differences in Go's implementation. So object-oriented programming is really for code organization. In my mind, it's for code organization. So you organize your code by encapsulating your code. You group together data and functions that are related to each other. So this is essentially what a type is, right? So, and what object-oriented programming lets you do is essentially create a user-defined type, one that's specific for whatever application it is that you're building, right? So typical types, you have integers, floats, that sort of thing. Those are generic, right? You can use those in any kind of program. But when you're making a specific application, you might like to have a type that is specific to that application domain. And you can create that. Object-oriented program allows you to create that. So if you think about a type, your standard type like an integer, each integer, it has data, right? The number, the value of the number. And then it has functions that you can apply to the data. So you can apply addition, subtraction, multiplication, that sort of thing. So a type has data and it has a set of functions that you can apply to the data. So object-oriented programming is the same idea. You are creating types, but they are more complicated. They can be more complicated, and they are specific to your application. As an example, you might have, let's say you're making an application, and it's going to do geometry, some kind of geometric operations in 3 dimensions. So many of the functions that you're going to write, are going to operate on points, right? You're going to have this idea of points because you're doing 3D geometry. And each point is going to have some data associated with it, specifically, X and Y and Z coordinates. Maybe you want to put other data in there, but at least you're going to have that, X, Y, Z coordinates, because in 3D. Also, points are going to have a set of functions, that you can use to operate on points. So distance from origin, distance to origin, right? Maybe every point has a distance to its origin. You can have a function that computes that. Quadrant, it tells you what quadrant, maybe it returns what quadrant the point is in, right? Something like this. There are a lot of functions that you can imagine that work on points. So if I think about this idea of points, I got a bunch of data that I want all related together. So I want the X and the Y and the Z variables for a particular point, I want them to be somehow associated together. Also, I'd like these functions that operate on points to be associated with that too. So in typical object-oriented languages, you have this idea of a class. And now I should note right now, Go does not use this term class. Okay, but I bring it up because it's used in other object-oriented languages, and so people might be familiar with this idea. So this class, it defines, maybe I'd make a point class. And the class defines all the data that would be inside a point. So X and Y and Z, maybe they're all floating point values, something like that. And the class would define all the functions that you would have that are associated with points, distance to origin, quadrant, and so on. So that would be the class, and then an object is an instantiation of the class. So I can make my point class, but then I might have many different actual points with actual data values inside. So if I have a triangle, right, I've got 3 points with 3 sets of X and Y and Z values. So I might have this point class that's sort of a general template of what a point should have, but then the point objects, my 3 point objects, will have actual values for X and Y and Z and so on. So that's the idea. That's the terminology that you normally see used, classes and objects, which are instances of that class. So different languages have this. Java, it's very popular. Java, Python, C++, and so on. Now in Go, we don't use this term class. Instead, they use structs. Now structs, actually this goes back to C and probably before that. But the idea of a struct is just the data. So the different types of data that you want to associate together. So like with our point class, you'd have a point struct, and it would have an X and a Y and a Z. Maybe they're all 3 floating points, right? So just the data related together. But also you can associate methods or functions with those structs. So the struct ends up being like what you would call a class in a normal object-oriented language. So you got these structs that have some data, some fields of data associated with them, plus some methods that you want to define. Now, Go's implementation of structs is simplified compared to traditional implementation of classes. So you don't have inheritance, you don't have constructors, and you don't have generics. None of those. Now, this, one can argue, makes it easier to code. Also, it makes it efficient to run, so it typically runs faster. But it can make it easier to code unless you like those features. Now, if you like inheritance and generics and constructors, then you could see this as a disadvantage. But Go is different than, it has objects, but is different than traditional object-oriented implementation. It's sort of a leaner object-oriented implementation. One of the big advantages of Go is its implementation of concurrency. So we'll talk a little bit right now about concurrency, what it is, and why it's useful, and how Go implements it, how there are built-in constructs in the language that make it easy to use concurrency. So I'm going to start by talking about performance limitations of computers. The reason for this is because a lot of the motivation for concurrency comes from the need for speed. Okay, a lot of the motivation, not all, but a lot of it does. So that's why I'm going to sort of introduce these performance limits on machines and how concurrency can help you get around these performance limitations. So Moore's Law. So just to summarize, you probably heard of this law, but in case you have not, Moore's Law, it basically says that the number of transistors on a chip doubles every 18 months. Now, this used to be the case. It is not the case anymore recently. That has changed, but this used to be the case. And so because of this doubling of transistors, what happened would be machines would speed up. Just because the transistors were smaller and they would be closer to each other, you could increase the clock rate. And so clock rates would just increase. I remember when I was in school, which was a while ago, you'd buy a machine and seriously a few months later there'd be another machine, same price, it was faster. And it was frustrating, okay? So these clock rates were just going up and up and up because the number of transistors were just increasing. Now, performance, that was great, right? And in fact, what that meant was that, I'm a hardware person. Mostly my background is a lot of hardware. And so I've always felt like software designers, programmers would get lazy, right? They'd write code, and it didn't have to be particularly efficient in terms of memory or in terms of speed because they knew that pretty soon hardware people would, double the number of transistors and fix all their problems for them, okay? So that's how it used to be, but that is not happening anymore because Moore's Law had to slow down. There are several reasons why. Probably the biggest would be the power consumption and therefore temperature constraints. So when you pack these transistors onto a chip, they generate heat. Every time they switch, they consume power, which generates heat. And if you keep increasing the clock rate, then they switch 0 to 1, 0 to 1 more frequently, higher rate, and they create more heat, and the chip will physically melt. Okay, so if you've ever opened up a machine, you see they got fans blowing over the chip. In fact, usually when you open up a box, you see on the box some big heat sink, big gnarly looking piece of metal that's actually attached to the processor that's just to distribute heat. So the air blows over it, the fan blows over it, and distributes the heat so it doesn't melt. So this is air cooling, right? And we are basically at the limits of air cooling. Air cooling can only remove so much heat per unit time. And so if you clock these things much faster with this density of transistors, you're going to melt the thing. So you can't keep increasing the clock rates. So it's a performance limit that's happening with machines. The clock rates are not going up as fast, as quickly as they used to go up over time. So how do you get performance improvement even though you can't just crank up the clock? So one way to do this is to use parallelism. So this is typically implemented, it's implemented in a number of ways, but you see this as an increasing number of cores on chips. This is one way that you see it, right? So you got quad core machines, these are common, right? They have 4 copies of the core on there, and you get more, right? Heck, if you go to a GPU, that thing might have 1,000 processor cores all in a massive array, right? So these cores, the number of cores on the processor increases over time. And that helps you because you can perform multiple tasks at the same time, potentially. Not always, but sometimes. If you got 4 cores, you can do 4 things at once, right? And that can improve your speed. You can get things done faster. Now, it doesn't necessarily improve your latency, but your throughput will improve, potentially. So difficulties with implementing parallelism. There are many, but programming-wise, there are difficulties. So for instance, when do the tasks start and when do they stop? A programmer has to decide this. For tasks, these tasks are not completely independent. So what happens when one task needs to get data that's generated by another task, right? How does this data transfer occur? Also, if you got multiple tasks running at the same time, do these tasks conflict in memory, right? They should not. You don't want one task to write to its variable A and that overrides variable B in another task. Right? So these are all problems that happen when you have concurrent execution going on. Because even if you got multiple cores, you got to worry about the memories, right? Are they sharing memories, right? Do they have separate memories? This is all, features of hardware, but the programmer has to often be aware of these things. And it's hard. So writing this type of code that can execute in parallel can be difficult. So in comes concurrent programming. Concurrency is the management of multiple tasks at the same time. So when I say at the same time, they might not actually be executing at the same time. Maybe they're executing on a single core processor, right? So they're not actually executing at the same time, but they are alive at the same time. So they could be executing at the same time if you had the resource, and they need to be sort of going on at the same time. So maybe one is paused while the other one's running, but they are all alive at the same time and need to be handled, at least from the user's perspective, at the same time. So this is key for large systems. There are big systems have many things, many pieces going on, and they're not all executing sequentially. You want to be able to consider 20 things at one time. Right now, maybe they're not actually executing at the same time, but you would like to have the possibility of executing them in parallel, if at all possible, just for speed, right? So concurrent programming, it enables parallelism, right? So if you can write code so that all these tasks can be alive, multiple tasks can be alive and communicating at the same time, then if you have the resources, the parallel resources, multiple cores, multiple memories, stuff like this, then you can map them onto those parallel resources and get parallelism. Okay, so you can't just take a regular piece of code and say, okay, I'm going to run it on 5 cores. That won't work. The programmer has to decide how to partition this code. I want this running on one core, this on another. I want this data here, this data there, and so on. So that's what concurrent programming is about. The programmer is making these decisions that allow things to run in parallel if the hardware exists. So concurrent programming includes several things. We'll go into more depth later in the concentration, but specialization rather. But management of task execution, so when a task starts and stops, how do 2 tasks communicate, send data back and forth, share memory if they share memory, and how do they synchronize? So there are times where one task has to do something before the next task can start. So there are times where 2 tasks can't be executed completely in parallel. There has to be some sequential behavior. This task can't start until this task ends, and so on. So that's synchronization, and you have to be able to manage that inside your programming language. The programmer basically has to express inside the code where synchronization needs to occur and where it doesn't. So that's what concurrent programming is, and it is important if you want to be able to exploit parallelism when it exists. So concurrency in Go. So basically, the thing about Go is that Go has a lot of concurrency primitives built into the language and implemented efficiently. So Go routines, each one of these Go routines represents a concurrent task, basically a thread. Channels are used for communication between concurrent tasks. And select is used to enable synchronization. These are just the high-level basic keywords that you can use, but we'll talk more about these later on in the specialization. But having concurrency built into the language and have an efficient implementation is advantageous if you're doing concurrent programming, which more and more, especially with all the cores that exist in processes these days, is becoming more and more important. We'll talk right now about how you download and install the Go tools, just to get you started running a program. Right now, we'll talk about the download process, and then next I'll go through actually doing it, showing you sort of how to compile your first program. But right here, just talk about installing, which is fairly straightforward. So first thing you're going to do is go to golang.org. And this is a snippet of the page when you go there. This isn't the whole page. I had to fit it on the slide, but this is what it basically looks like. At least right now it does. That can change over time, of course. You can see the gopher. See that little gopher? You'll see that gopher icon over and over again. Gopher is, the mascot of the Go programming language. Like Unix, you got daemons, right? So Go, you have the gopher. But the main thing to look at here is that button down there that says Download Go. So that's the first thing you're going to click on. You're going to say Download Go. You click on that. And as long as we're looking at this, on the left side, when you go to the web page, you'll see the whole screen. I've cut it off here, but on the left side, you can see there's a yellow box there where you can type in Go code and click on the Run button. It'll compile and run it. So it'll compile it remotely and run it remotely. We're not going to use that. Instead, we're going to download the compiler. We're going to download it to your machine locally, and you'll be doing it locally. But if you want to just fool around, you could type some Go program in there, click Run, and it would actually execute it. So what we're doing, though, is we're going to click Download Go to download the tools. Now, when you do that, you come to a page that looks like this. Now, again, I'm only showing a part of the page. There's more below it and to the right. Basically, when you download Go, you can download the precompiled versions for different platforms. They've got Windows and Linux and Mac OS. And you can also download the source. Download the source if you want to. And you could compile all of Go from scratch, this whole tools chain from scratch if you wanted to. We will not be doing that. That is pain. We won't be doing that. But know that you could. It is open source and all the source is right there for download if you want it. So I'm going to be doing this on a Windows machine, although you could be doing it on a Linux or a Mac OS machine, either way. So go for the featured downloads. They make it pretty easy. For Windows, you pick that MSI file that they've got highlighted right there. Basically, what you want is the newest stable precompiled version. Don't go for I don't see unstable ones on here, but I recommend the stable, but it's up to you. Anyway, you go for a new version, click the featured one, and you download this MSI. Now, once you get that, and remember, there can be, if you have an antivirus on your machine, it can pop up and worry about this and complain. But just say okay. And then once you start running it, it'll start a wizard. Now, you've seen these installation wizards, and this is sort of a standard installation wizard. Just obey the wizard and click next, and it'll ask you where you want to install the tool, what directory you want it in, and so on. The default locations were fine with me, but that, of course, is up to you. Right now, we're going to talk about how code is organized in Go. First, we'll start with a workspace. So there's this idea of a workspace. And it's basically a directory where your Go stuff will go. So your Go files, your Go source files and other files will go in this workspace directory. And typically there is actually a hierarchy of directories within your workspace where you will store the different types of Go files that you're working with. Now, the reason why we're doing this, why the Go language defines this hierarchy of directories is because common organization is good for sharing. So a big motivation behind Go, the Go language, is for people to work together easily. So remember that when you're programming, not necessarily in this class. In this class, you're working on learning the language, the different aspects of the language. But when you get outside and you're working in a company or something like this, it's never one person alone. It's always a big group, right? You're working with people all over the place. And they have to be able to work with your code. Look at your code, merge it with their code, link it to their code, that sort of thing. So there's always this sharing going on. Maybe you want to upload to GitHub and have a communal group of people working on code together. So for that, it is nice to have a common, standardized organization of your files, right? It makes it easier to share because then everybody knows where everything is. Tools know where things are, stuff like that. So inside your workspace directory, what is recommended are these three subdirectories. The source directory, it contains the source files, your source code, your Go code. Package directory contains packages, the other packages that you're going to link in that you need. And then the bin directory that contains all your executables, your compiled executables. Now, the programmer typically has one workspace for many projects. So I typically use my one workspace directory. And I can have 20 projects, 20 different Go projects I'm working on in the same workspace directory. That's common. You don't have to do that, but that's common. So one thing to remember about this directory hierarchy is that it's recommended, but it's not enforced, okay? So this idea of having the source subdirectory and the bin subdirectory and the package subdirectory, that's not, it's not enforced. So for instance, you can have an executable in the source directory if you want. It is not neat and it's harder for people to share, but it's going to run. You can compile it and put it anywhere you want and run the executable, right? So it's not enforced. It's just this is a recommendation to make it easy to share with other people. So the workspace directory, you do have this one workspace directory though, and this workspace directory is defined by the GoPath environment variable. Now the GoPath environment variable depends on what, how you set environment variables is going to depend on your operating system. Normally what happens is, like on my Windows machine, but this should happen on a Linux and an OS X machine too, is that the GoPath directory is set for you automatically during the installation process. So that wizard, that install wizard, it should define the GoPath environment variable. And certainly on a Windows machine, the default directory where it puts it is C:/user/your name. So for me, /user/Ian/go. It sets that as your your workspace directory. Now, I noticed that when I installed everything, that was my Go path. What you see up there, users/en/go. But it actually didn't create a Go directory. So there was /user/en. I had to create the Go directory myself, which is fine, but I had to make that directory and put my stuff in there. But understand that that's the default workspace. You can change that. You can go to your Go path environment variable and change your environment variable in your operating system if you want to. But for now, I'm just assuming that we're using the default Go path. So the Go tools all assume that the code is inside the Go path somewhere. Now, there's this other concept of packages. Your code is organized into packages. A package is a group of related source code files. Each package can be imported by other packages. So this is the use for this. The main use for this is when you're working with other people, other groups of people in other places. You write all your code in one package, they write all their code in another package, and then if you need to use their code, you can use their code, you can import their package. So actually I have, so it's good for software reuse. That's the main goal. And the first line of the file names the package. So what I'm showing here in the picture, you can see these two pink boxes up here. These are two packages that are defined. And you can see the first line of, so those are two different files, two different source code files. And you can see the package names are listed at the top. Package, right? And there's a bunch of code in there, and they're all they're associated with that package name. Then in blue, I have some other piece of code in a different source file, and it needs to use the packages from the other two people, right? So I have an import statement at the top of my blue file, and I give the package names that I want to import, so I can use these other two packages in my code if I want to. So this is how packages get connected to each other. And it's very convenient if you're working with somebody remotely or somewhere else. It's sort of a clean separation of the code. Now, there always has to be one package called main. And that's where execution starts. So there's got to be one package called main. And you'll note that in the code that we're working on in this course, we just have one package, and it is called main. Okay, because we're not making such big code that, where you have different groups of people working together with different packages. Right now, we're just writing one package called main. But there must be one package called main, and when you build the main package, when you compile it, it makes an executable of that. So note that when you build another package, the non-main packages, then it doesn't make an executable for those, right? Or not a running executable, because it's not going to be executed directly. It'll be incorporated into some other package. But the main package, that's what's going to be run. So when you compile that, when you build it, build/compile, you get an executable file. So the main package needs to have a function called main, and main is where code execution starts. So you can see the example code right here. It's just printing hello world. We say package main, import format. So that import right there is importing a package. Format is not a package that I wrote. Format is one of the packages that comes with the Go tool. So when you download the Go tools, you get all these standard packages, including format. And the format package has a lot of functions in it. We'll talk more about it later. But one of the functions that it has is this print statement. So printf is included in the format package. So we have to import that package. And then we make our function main. And in there, it just says format.printf hello world. So pretty straightforward. So we're going to talk about the Go tool a little bit, just overview it really. It has a lot of features, and we'll get to those over in different courses actually during the specialization. We'll talk about a little bit of it now, but let's start off with import. So just to restate what import does, it's a keyword and it's used to access other packages. Okay. Now, for the most part, the packages that we're going to be importing will be the built-in packages, the ones that come with the Go language, to implement different functions that we're going to use in the course. So, for instance, right now, like right off the start, we're going to use this format package, FMT, and it has a printf statement built into it, and we use it for printing things. Now, what happens is when you do an import, the Go tool, when it does a build, it has to find the imported packages. So it searches through the directory specified by the go root and the go path environment variables. So if you keep everything inside your go path and your go root, so inside your workspace, it'll find them. If you decide you want to import some package from some other place and maybe it's installed in a different directory, something like that, then you're going to have to change your go path and go root paths. You're going to have to increase them, change the path, change the environment variables so that it can find them. But that won't be a problem for basically the majority of this course, right? We're not doing that. But I'm saying in the future, when you're working with really big code, you might need to alter these environment variables in order to be able to find the packages that you're looking for. So the Go tool. When you download Go, you get this Go tool, and it's a general tool used to manage Go source code. There are many commands, a bunch of different commands that you can use the Go tool to do. The first one is going to be go build. So that is just compiling the program, right? The arguments to go build, you can have no arguments, in which case it just compiles a Go file in the local directory. But you can give it a bunch of packages, a bunch of package names, or a bunch of Go files that you want to build. You can give that as the arguments to this go build command, and it'll go build whatever you tell it to build. Or you could just say go build. That's what I did in the demo. I just said go build, and I was already in the directory where I had my main package, and so it just compiled that. So it creates an executable for the main package, and the executable has the same name as the first .go file. So if you're just using one .go file, you're just going to get that as the name. The .exe suffix is what you're going to see for executables in Windows in general, right? So you'll expect to see a .exe in the executable, and that should be in the directory where you did the build. If you give it no other arguments, it'll just place it in the same directory. Now, there are tons of arguments to these commands that I'm not really going to go through, but you can have arguments where you can tell it to build and put the executable in a different directory and so on. I'm not going to do that right now. We'll finesse that stuff later. So some of the other Go tool commands, just go through these a little bit. Go doc. Go doc prints documentation for a package. Now, we'll go over this later. But you have to, as a programmer, you have to put the documentation in your package, and GoDoc will just pull it out of all your packages and print it. Go format. That formats source code files. So we're not going to get heavily into this, but if you program at all, you must have heard arguments about, oh, you need this type of indentation and stuff like this. So this Go format will just indent it the way it should be done, okay? You just give it the source code file and it'll indent it right to get past all those arguments, right? There's a standard indentation. You don't have to use it, right? Remember, the indentation isn't forced on you. This isn't Python or something like that. You don't have to, but Go format will do it for you, so why not? Go get downloads packages and installs them. So if you want to get new packages that do interesting things that aren't standard default packages, you can say go get and give the name of the package. It'll go online, find the package, download it. Go list install all the installed packages. Go run compiles the Go file and it runs the executable. So if you just say go build, that compiles it and does not execute it. But go run actually compiles it and then executes the executable in the end. Or if it's already compiled, it'll just run the executable. Now, you don't need go run. You can, like in my demo, I think I did a go build to get the executable. I think it was called hello.exe. And then I just typed hello.exe at the command line and it executed it, right? So I didn't have to use go run in order to run the executable, but you can. And go test, actually the last course, the fourth course in this specialization is actually about testing, and we'll get to that then. Go test, it runs tests. And it looks at basically you have a bunch of test files that end with this _test.go, and you can run these tests using the go test command, but we'll cover that later. So now we're going to start talking a little bit about the Go language. We'll broach the topic of variables and talk a little bit about those. Variables are in every high-level language, and we'll just see how Go implements it. A lot of this is very similar to what you've seen in other languages. Some things are a little bit different. So first there's naming. Every you need names, names for variables, for functions. You need names to refer to things in your code. So names for variables and things like that, they need to start with a letter. They can have any number of letters and digits and underscores. They are case sensitive in Go, and you can't use keywords. There's a list of keywords. You can Google these or look them up. But if, case, package, all the different keywords of the language, you can't use those as the names. So variables are basically data stored in memory somewhere, and every variable has to have a name and a type. So all variables have to have a declaration that specifies the name and the type of the variable. So so here's a really simple variable declaration. It just says var x int. So var is the keyword for a declaration of a variable. After that, I have the name. So my name of a variable is called x. And then after that, I have the type, var x int. That's it. That's a declaration of this variable x. It says it's an integer. And the compiler needs to know what type of variable it is, what the type is, so it knows how much space to allocate, what operations to perform, that type of thing. You can declare many on the same line if you want to, just comma separated, so var x comma y int, and you can do that as much as you want. So variables have types. Type defines the values that a variable can take and the operations that can be performed on that variable. So for instance, common types, basic types, integer, floating point, and strings. Integers, the data, the variables, the values that they can take are only integral values, right? They're integers. And the operations you can perform are integer arithmetic, plus, minus, times, that sort of thing. And there are a set of other ones. We'll talk about them in a little more detail. Floating point. Those the data that they can have, the values that they can have are fractional, right? Decimal values. And there you have a set of operations, arithmetic operations. Actually, they look superficially the same as the integer operations, plus, times, divide. But they may actually be implemented with different hardware, right? Because a floating point division, say, is significantly more complicated than an integer division. So oftentimes there's special hardware just for floating point divide and things like this. We don't have to know that as programmers, but the machine has to know which operation to map it to. Then strings. So strings, they're a sequence of bytes represented in Unicode, and we'll get into that later. But it's a sequence of bytes. That's the type of data, the values they can take on. And then the operations you can perform on strings. There are many of them. String comparison, string search, concatenation, all sorts of operations that you can perform on a string. But the point is, the type specifies these things. It specifies what data the variable can hold and how big that data can be, right? Because you need to know how much space and memory you're going to need to allocate for this. The compiler needs to know that. And also what operations are going to be performed on it. So what that's for is, eventually, the compiler is going to have to take these operations that you type in Go and compile them into machine code instructions for whatever the hardware platform is. And those machine code instructions can be different depending on the type. So for instance, you can easily have an add for an integer add machine code instruction, which is different than a floating point add, right? Integer division, which is different than floating point division, and so on. So this is why the compiler needs to know the types so it knows how to do the compilation and how to convert it into machine code. So we're talking about variables, and we're going to talk about how you initialize them. But first, let's finish up the types. So every variable has to have a type. And you can make type declarations where you actually define an alias, an alternate name for a type. So sometimes this is useful for clarity inside a particular application. For instance, here, where it could help you, say you got some kind of application, and it's working on temperatures. Temperatures are something that's manipulating, right? And every temperature, you want it to be a floating point value, 64-bit floating point value. So you can define a new type, or an alias for a new type Celsius float 64. In that case, Celsius is exactly the same as float 64. Now, you can always declare your variables to be float 64, but Celsius might make sense in the context of the application, right? Maybe the application is about temperatures, so maybe you want to rename it just to make it clearer for you as a programmer. Also, like the next one, type ID num int. Maybe I want to, this, I'm making some code that implements a database of users or something, and every user has an ID number. So I know this concept ID number. I know it's an integer, but I want to name it. I want to give it that name ID num so that I know every variable that I declare as an ID num, it is an ID num. I know something about it just based on the name of the type. So once you declare a type like this, type Celsius float 64, type ID num int, you can now declare variables using that alias. So I can say var temp Celsius, right? And now temp is going to be a float 64 because 64 is just float 64 is aliased by Celsius. Also var PID ID num. PID is actually an integer, but we call it an ID num, and it makes things more clear. So initializing variable values. Every variable has to be initialized somehow before you use it. One way to initialize it is in the declaration itself. So you can say var x int equals 100, and that will make x an integer. It'll declare it as an integer, but it'll also set it equal to 100. Or you can just say var x equal 100. Now, if you do that, you're not saying you want it as an integer. So it will infer the type. The compiler will infer the type based on the type of the right-hand side value. So the number 100 is an integer, so it says, oh, x must be an integer. It makes it an integer. Now, remember, sometimes this is an issue because maybe it infers something that you don't want, right? I like to specify it myself, but maybe. So for instance, say I say x equals 100, but I really want it to be a floating point. I mean, 100 point something, right? But I call it 100 because that's my initial temperature that I want, but I want it to be a floating point value. This will, if I don't specify, it'll say, well, 100 could be an integer. It'll infer it as an integer. And then if I try to set x to 100.1, I'll have a problem. Now, so I like to specify the type, but you don't have to. Next up, initializing after the declaration. So you can just say var x int, and then afterwards you can say x equals 100 and on a following line. And that's another way. Now, if you don't explicitly initialize a variable, it will still get a value. It'll get the 0 value for its type. So for instance, say I say var x int. The 0 value for its type is 0, right? So x will be automatically assigned to a 0, initialized to a 0, if I don't say anything else. If I say var x string, the 0 value for a string is just the empty string. So x would be initialized to the empty string in that case. Now, another way to initialize variables is using a short variable declaration. Now, in this case, you're performing the declaration and the initialization together using a colon equals operator. So, like there, up on the slide, x colon equals 100. Okay. When you say that, this is a case where x has not been declared yet, right? So this statement actually declares x and assigns it, initializes it. Now, the declaration, what happens is when you use that colon equal, the type that it sets it to be is whatever's on the right-hand side, so 100 in this case. It looks at 100, says, oh, that's an int, and it infers x to be an integer. And then it assigns it to the value 100. So variable is declared as a type of expression, the type that's on the right-hand side. So it does this type of short variable declaration. It does the declaration and the assignment together in one line with this special operator. You can only do this inside a function. So you can't do a short variable declaration outside a function. That's not legal. So just know that. Welcome to the second module. We're going to start talking a little bit more detail about the Go language. We'll talk about data types in Go, the basic data types. That's what this module is really about. We'll go over data types that you've seen in other languages: integers, floats, booleans, strings, variations on those. So you can change the length of the integer, length of the float, things like this. So we'll talk about those data types. We'll talk specifically about how to declare them, how to create them, and what functions are available for them. So what functions can you apply to integers? What functions can you apply to strings and booleans and floats? And once you're done with this, you'll be able to use basic data types inside your Go code. So in this module, we're going to talk about basic data types, and we're going to start with pointers, which maybe is an unusual place to start the discussion of data types, but that's where we're starting, because people who are taking these courses generally already know something about programming. So let's go straight to these pointers and talk about them. A pointer is an address to some data in memory. So like I was saying, every variable is located in memory somewhere. It's some data sitting in memory somewhere. Also functions and so on, they're all in memory somewhere. A pointer is the address of that in memory. Typically a virtual address, but that doesn't matter to us too much right now. So with pointers, there are two main operators that are associated with pointers. The ampersand operator right there, that returns the address of the variable or the function, whatever the name is referring to. And the star operator, which is dereferencing, does the opposite of the ampersand. It returns the data at the address. So the ampersand operator, if you put that in front of a variable, the name of a variable, that will return you the address of that variable. The star operator goes the other way. If you put that in front of a pointer, right, to some address, put that in front of an address, it will return you the data at that address. So it's important to understand that this ampersand operator and the star operator are opposites of one another. So to give you an example, let's take a look at this code, little piece of code. We define our variable x is an integer. It's equal to 1. And then y, it's an integer and it's not initialized, so that would mean it would be by default initialized to 0. Then a var IP. So IP it's not declared to be an int, it's a star int. Right? So that means IP is actually a pointer. Since there's a star operator in front of the int, IP is declared to be a pointer to an integer. So IP is the pointer, but it is not an actual integer. It is a pointer to an integer. So then if we go on, IP equals ampersand x. X is actually an integer, right? Integer whose value is 1. So there is a number 1 sitting in memory somewhere, and x is a reference to it, the name of that. Ampersand x is the address in memory where I can find that value 1. So IP is now equal to that address. So whatever the address of that 1 is, of x, whatever that address is, IP is the pointer to that address. It is the address. Now then in the next line I say y equals star IP. So remember that in this little example, IP is actually a pointer, and the data at that address that IP is pointing to is the value 1. Now star IP, star does dereferencing. Star returns the value, the data at that address. So y is now equal to the data at the address that IP is pointing to. Now if you remember from the line before, IP is pointing to what x is pointing to, right? So IP is pointing to the value 1, that data in memory. So if y is equal to star IP, y is equal to 1. So this now sets y equal to 1. It's just a little example here, just trying to show how the ampersand and the star operators work opposite to one another. So these are pointers. And pointers exist. These pointers are basically, if you know C, same type of implementation. Now, there's another function called new. It's another way to create a variable. And new returns, instead of returning a variable, it returns a pointer to the variable. So the new function creates a variable and it returns a pointer to that variable. So this is unlike if we were just declaring a variable, right? That also creates a variable, but new explicitly returns a pointer to a variable. So the variable is initialized to 0 by default with new. So for instance here, if I say pointer equals new int, and then star pointer equals 3, right? Pointer equals new int, new int returns me a pointer to an integer, and that PTR is equal to that pointer. Then I can set the value of that integer by referring to star PTR, right? Because star PTR is the value that PTR is pointing to. If I say star PTR equals 3, then the value 3 is placed at the address specified by PTR. So we're going to talk about what the scope of a variable is. Roughly, the scope of a variable is the places in the code where a variable can be accessed. Okay, so variable scope defines how a variable reference is resolved in the code. So if you reference a variable x, how does the program figure out which variable x you're talking about? Okay, that's basically what variable scope is. So in these little examples, just to show you an example of scope, if we look at the first block of code, we got this variable x that I'm highlighting in red, right? And this variable x is defined outside of these two functions. So I've got these two functions defined, function f and function g, right? But outside of both of them, I've defined this variable x. So var x equals whatever it is, 1. Then I define my function f and function g. Now, if you look inside function f and g, they're very simple. All they're doing is they're printing x. They're both printing x. That's all they're doing. So inside function f and inside function g, when you call these functions, they've got to figure out where to find the value for x. Now in this case, they're going to find the value that I've defined outside. So where I say var x equals 1, when they print out x, they're going to print out 1 for x. Because the scoping rules allow that. So basically because it's defined outside of either one of these functions, both of them will have access to it. And we'll define the formal rules for that in a few slides. Now in the next block of code, you get a problem. Because in the next block of code, again, you've got function f and function g. But this time, variable x is defined inside function f, but not inside function g. Right? It's only inside f. So function f will print properly because it'll look at x and resolve it. Since it's defined locally right there inside its function, it'll say, oh, x is equal to 1, and it'll be happy. But function g will have no reference to x. It won't be able to see that, and it'll throw an error when you try to run that because it won't know what x is. So this is the type of problem that needs to be resolved. You don't want to run into this type of problem. You want to be able to know where your variables get resolved to, and so that you don't have problems like this. So we're going to talk about variable scoping right now. So how does a compiler figure out, where a variable reference should be resolved to? Which x are you talking about? Is it this x or is it that x? So in Go, variable scoping is done using blocks. Now, a block is a sequence of declarations and statements within matching curly brackets. So those curly brackets right there, you have an open curly bracket, close curly bracket, everything in between is called a block. So that's how you explicitly define blocks. And you notice how these blocks can be hierarchical, right? You can have curly brackets, and then within that you can have some other curly brackets. And within that you can have some more. So you can have this hierarchy of blocks. And these are explicit blocks. When you put the curly brackets in your own code, those are explicit blocks that you as a programmer included. Function definitions, notice, are defined by curly brackets, right? We haven't gotten to functions. We'll talk about it more later. But every function definition, you define the function, give the name of the function, and then you have open curly brackets, close curly brackets. So every function, you've got curly brackets. So there's a hierarchy of these curly brackets and a hierarchy of these blocks. Now, also, there are implicit blocks inside this hierarchy. So there are blocks that are implicitly defined without the curly brackets. So just to list those blocks. First is the universe block, right? That's all Go source code. That is the biggest block, the universe block. There's a package block. So every package, even though you don't put curly brackets around every package, all the source code in a particular package, that's all within one block, which is inside the universe block. Then there's a file block, right? File block, all the source code in a single file is within the file block. And remember that a package can be composed of many files, right? So there can be one package block that has many file blocks if you've got a lot of files inside the package. Now, then other implicit blocks include the if statement, for statement, and switch statements. All these have curly brackets that define their own blocks. Also, the clauses inside a switch are select. We'll get to these in more detail later, but these are all the ones I'm listing here are these implicit blocks that you don't have to put explicit curly brackets for. So you can. So for instance, in an if statement, you can use curly brackets too, but like the universe block, the package block, file block, these are all implicit blocks, and there's a hierarchy of these. So that's my point. That there's this hierarchy of these blocks, and each block can have its own environment of variables associated with it. Okay, so lexical scoping. This defines how variable references are resolved. So Go is a lexically scoped language using blocks. So when we talk about lexical scoping, we've got to talk about this relationship of being defined, one block being defined inside another block. Okay. So I'm using this terminology here. I'm saying BI is greater than or equal to BJ. If BJ B is a block. Okay, if bj is defined inside bi, then bi is greater than or equal to bj. Okay, so I would say that bj, if it's defined inside bi, bj would be, you refer to it as an inner scope, where the outer scope that includes bj is bi. Okay, so just as an example of this, it's a transitive relationship, but just as an example of this, look at the code. We got, we've seen this code before. We got variable x. We initialize that to 1. Then you got function f and function g. Now, if we look at the blocks inside here, first you've got, this is all in one file, right? So all of this is inside the file block. And I'm calling that B1. So B1 is my file block, and everything is inside the file block. But in addition to the file block, I'm defining two functions, f and g. And each one of these functions gets its own function block. So B2 is a function block for f, and B3 is a function block for g. So if I were to look at how these blocks are related, B2 and B3 are both defined inside B1. So I'd say B1 is greater than B2. And B1 is greater than B3 by my definition, because B2 and B3 are defined inside B1. But notice that there's no relationship between B2 and B3, because they're not defined within each other. Okay? So we need to know this, because the scoping rules, when you're resolving a variable, you go to the greater including scope. So for instance, if inside B1, the function f, right, inside that block, you're referring to variable x, then it's going to look for that variable x inside B2 itself, inside its local block, but then it looks for the next bigger block that is defined inside. So it starts in B2, looks for variable x. If it doesn't see it there, which is not defined there in this case, then it says, okay, what is the next bigger block that I'm defined inside? It would get B1, and would look inside B1 and say, there is a definition of x here, and that's the definition of x that it would use. Same goes for B3, right? And if you look at the function g, it uses variable x. It acts as variable x. First it looks inside its local block, B3. It doesn't see it, so it looks inside the next bigger block that is defined inside, B1, and it sees it there. So that's why this works. That's why this code will work. The x will be resolved properly to that x equals 1, that variable that we defined inside B1. So when you're talking about scope of variables, a variable is accessible from a block, bj, if the variable is declared in some block bi, and block bi is greater than or equal to bj. So it's either the variable is either declared right there in bj, or it's declared in some outer block that's greater than bj. So that's why in the first block of code, the first code sequence, you can see where x is defined inside the file block. Both of those functions, which are also inside the same file block, they can both properly access the x variable, because their function blocks are within the file block. But in the next block of code, next sequence of code, the x is defined inside the function block of f, but it's not inside the function block of g. So when g tries to reference x, the variable x, it doesn't see it in its local block. It also doesn't see it in its file block, right? Because now the definition is inside the function block for function f. So that's why this fails. The x doesn't get resolved back to anything, and there's an error. So we've been talking about variables and how they're referenced. Variables, they're all referring to some data that's somewhere in memory. So the variables eventually have to be deallocated in memory. So allocated and deallocated. So what I mean is, once you declare a variable and your code is running, space needs to be allocated somewhere in memory for that variable. If it's an integer, there has to be some allocated space dedicated to holding that integer. And at some point, that space has to be deallocated when you're done using it, right? So when you're done using your variable x, you want to be able to say, that space is now free and it can be used for other purposes. So that's deallocation, when you make memory space available for other purposes. You have to do this in a timely fashion. So otherwise, you eventually will run out of memory in your machine. So for an example, if you look at this piece of code, it declares a variable x, var x equals 1. So the process, when it runs, it has to allocate a memory location just for X to hold it. Now, say you call in your program F, you call this function F 100 times, right? Then it's going to allocate 100 different spaces for this variable X, right? Because the X goes away after the function completes. The X goes away, it's going to allocate it again. It should go away. You want it to go away. But every time, if you don't deallocate it, you'll execute, every time you execute this function F, you'll get a new variable X allocated. And so you'll have all these spaces allocated in memory, and really you don't need them anymore, right? I mean, once a particular function call ends, you no longer need the space that for the X that it was using. So at some point you have to deallocate this memory. You have to say, look, this memory is now free, because otherwise you would eventually use up all your space. And you might think, well, how am I going to use up my space? I've got X number of gig in my memory system. You can eat that up very quickly, right? And believe me, this is called a memory leak. This is a thing that happens in C a lot. You can eat up all your space very quickly. So you have to deallocate this space in a timely fashion. Now, in order to talk about how space is deallocated, we got to talk a little bit about where the space is stored in memory. So memory is a big thing, but there are two big hunks of memory that are relevant to us right now: the stack and the heap. Now, the stack is an area of memory that is dedicated to function calls, primarily dedicated to function calls. So one of the things stored in the stack are the local variables for a function. So every time you call a function, there can be variables that you define in that function, and generally they go into the stack. They are allocated in the stack area of the memory. And they're deallocated. If they're allocated in the stack, they are deallocated automatically when the function completes. Now, this is different, a little bit different for Go. This is traditional. What I'm talking about now is how it works in regular languages. Go changes this a little bit, okay? But normally, the stack is the area of these local variables where when the function is done, the variables are deallocated automatically. Now, the heap, on the other hand, is a persistent region of memory where when you allocate something on the heap, it doesn't go away just because the function that allocated it is complete. That heap memory, you have to explicitly deallocate it somehow in another language. So if you were in, say, C, you would have to explicitly deallocate this. Now, Go does a tweak on this, but it is still important to understand that memory variables can be in the stack, which will, for the most part, automatically go away when the variable, it'll be deallocated automatically when the function is done, or in the heap where it's persistent. Now, if you're in another language like C, then you have to manually deallocate things on the heap. On the stuff that's on the stack, you don't have to manually deallocate it. It'll go away when the function completes. But the stuff that's on the heap, you have to manually, explicitly deallocate it. So, like, say you were working in C, if you want to allocate memory on the heap, you would call a function called malloc, and say x equals malloc 32. It'll allocate 32 bytes of memory, and x will be a pointer to that. And then later, that's how you allocate it. Later, when I want to free it, I can say free x, and it will free that space, deallocating it. So error prone but fast. So what I mean by that is it's error prone because it's easy to make a mistake in your allocation and deallocation. Deallocating at the wrong time or forgetting to deallocate it, stuff like this, it can cause you headaches. And it's error prone in that sense, but it's fast, right? The implementation is very fast. You don't have to see what happens with deallocation, like in an interpreted language, is that the interpreter does it, okay? And that can take time. So, but in a compiled language like a C, you would have to do that manually. So we've been talking about deallocating memory, and it can be hard to determine when it is appropriate to deallocate a variable. Reason is because you can only deallocate a variable when you know the variable is no longer in use, right? You don't want to deallocate a variable and then later need that variable that you deallocated, because then it's basically gone, right? So it's hard sometimes to figure that out, figure out when it's not in use or when it is in use and so on. So here's an example, a Go example, this is legal in Go, but because this is a pain, this is not legal in certain other languages. But in Go, this is a legal thing. If you look at the first function, foo, inside there we declare this variable x. So it's a local variable to this function foo. And what's returned, though, is the address of x, ampersand x, right? A pointer to x. Now then in the main function down below, the main function calls foo. And then the main function, what happens is, since it calls foo and it uses, it gets the return value of foo actually gets assigned to a variable in the main function. So the trick here, the confusion here, is that this program foo, normally if you declare a local variable x, when the function ends, that variable x should be deallocated, right? You're done with it because the function is done with it. But in this case, it's not the case because it's returning a pointer to x. So now the main, since the main now has that pointer to x, since that's getting returned to the main might still use that pointer to x. So you can't just say, oh, well, foo is now done, I can get rid of its local variable x, because maybe main is going to use that local variable because now main has a pointer to it, okay? So this is actually a legal thing to do in Go. So this is just one example of how pointers especially make it difficult to tell when deallocation is legal and when it's not. So deallocation is a complicated thing. So what people do, one way of dealing with that is to have garbage collection. So garbage collection is basically an automatic tool that deals with deallocation. So this is part of interpreted languages, and it's done by the interpreter. So if it's, say, Java, the Java virtual machine, or in Python, it's the Python interpreter, something like that. And it keeps track of these pointers, and it determines when a variable is not in use anymore and when it is. And once it determines that a variable is definitely not in use, there are no more pointers, no more references to that variable, then the garbage collector deallocates it, only when all references are gone. So this is nice. Garbage collection is a nice thing. It's easy for the programmer, right? Programmer doesn't have to worry about exactly when deallocation, when to do it, when not to do it. Believe me, deallocating memory is a big headache in other languages, say C or something like that. But it requires an interpreter. So generally, compiled languages like C, C++, they can't do it. But Go is different, okay? Go is different and better in this sense. So Go is a compiled language which has garbage collection built into it. So that is a unique feature of Go, which is really nice. So as a result, the Go compiler can figure out it can figure out when, like, it can follow these pointers to some extent and figure out when this pointer is still in use. And it basically keeps track. We're not going to go into garbage collection because that is a complicated thing. There are many ways of doing it, but generally you have to keep track of the pointers to a particular object. And once all the pointers are gone, then you know that the object can be deallocated. And so garbage collection in Go allows actually two things. One thing is it'll actually allocate stuff on the heap and the stack itself. So you as a programmer don't have to determine, I want to put this on the heap, I want to put this on the stack. The Go compiler, it'll put code in there. At compile time, it'll figure out this needs to go heap, this needs to go to the stack. And it'll garbage collect appropriately. So if it's on the heap, it will garbage collect it appropriately. It'll see when all the pointers are gone, and it'll determine when it can be garbage collected, when it can be deallocated. And this is a really helpful thing. Now, there is a downside because the garbage collection, the active garbage collection, does take some time, right? So there's a performance hit. But it's a pretty efficient implementation, and garbage collection is so darn useful, it's probably worth it to put it in Go. So that's a trade-off that Go makes. It slows things down a little bit, but it is to great advantage because it makes programming a lot easier. And you don't have to go as far as using a full-on interpreter like you would in an interpreted language. So we're going to continue talking about the basic data types, but a couple of things I want to hit on are comments and print statements. So it's interesting when teaching a class about programming language, there's some things that you have to teach it linearly, right? One thing at a time. But some things are basic concepts that I have to use very early on. So I'm going out of sequence a little bit, but these are comments and print statements I use all the time. I've even used them already. So I need to define those, then I'll keep going with the variables. Okay, so Comments. Comments, this is pretty straightforward. These are basically C-like comments. They look like it's the same as in C. Single line comments are just a double slash. So slash slash. Everything to the right of the slash slash on the line, that's a comment, which means it's completely ignored by the compiler. It's only text for the programmer to look at, to understand, to help with the understandability of the code, which is a useful thing. Okay, comments are excellent things when used appropriately. But you can see here, you can just say slash slash, this is a comment, and then everything to the right of it, which is everything on that line, is going to be a comment, stuff I've highlighted in red there, right? Then on the next line, I declare a variable var x int, and I say slash slash another comment. In that case, the slash slash, everything to the right of the slash slash on that line is comment, but the stuff on the left is still valid code. So the stuff on the left gets compiled, the stuff on the right is ignored by the compiler. Now, in addition to these single line comments, you got block comments, and those are marked off with the slash star and the star slash. So slash star begins that, star slash ends it. Everything between the slash star and the star slash is comment. So in this case, it's just 2 lines, but I could have any number of lines of code. If I wanted to have lines of text, whatever, I could have any number of lines of text describing a function or something like that. Mark that, put that as a block before the function if I wanted to. So those are comments. Now, an additional thing that I've already been using are print statements, just because they're so useful. Printing, it's done using the format package, FMT package. So you have to import the format package, import format at the top of your program. Then printf is sort of the first standard print function you use. Format.print, it prints a string. So you pass a string as an argument to printf. So format.printf quotes high. A string is delimited by these double quotes. And we'll talk more about strings, but the simple way is just double quotes. Or I can say x colon equals Joe, and then format printf high plus x, right? So plus is a concatenation operator that concatenates the high and the next string x, right, which is the word Joe. So that would print out hi Joe with space in between. Now we're going to use format strings. Format strings are strings that are used for formatting the output to make it look nice. And basically all format strings they're strings, double quotes, but inside the string use what are called conversion characters. So in this language in Go, they use a percent, and then some other characters. So for instance, if you look at the example, format printf says hi and then %s. %s is a conversion character for a string. So what's going to happen is wherever you see the conversion character, that character will be substituted by some variable. In this case, since it's %s, that means a string. So it expects a string. So if we look at the arguments to printf, the first argument is the high is the string high %s. That's a format string. The next argument is the x. That x is going to be some string that is going to be substituted in for the %s. So if x is the word Joe, then when I do this print statement, it's going to say hi Joe, right? Because Joe will be substituted in for the %s. So this is commonly used, these format strings are commonly used to make the format look nice when you're printing. So besides the comments and the printing, let's start talking a little bit about integers and the nature of integers. So first there's a generic int declaration. We've already declared some integers, var x int, right? Now there are different varieties of integers. Generally, for the most part, we're not going to care. We just say var x int and leave it to the compiler to figure out what type of integer, what length of integer to use most of the time. But you can have different lengths of integers. So for instance here, you got int 8, int 16, int 32, int 64. And those numbers are the number of bits that are used to represent the integer in memory. So 8-bit integer, 16-bit, 32-bit, 64-bit. Then uint are unsigned integers. So and also 8-bit, 16-bit, 32, 64. The difference between ints and uints are unsigned. So that means that they can get larger. Meaning normally we're using 2's complement arithmetic inside our machine. So the most significant bit is the signed bit. In an unsigned integer, that most significant bit is not used for the sign, it's used for magnitude representation. So the magnitude, the absolute value of the unsigned integer can get bigger just because you have that extra bit that would have been used for a sign in a regular integer, you can use it for magnitude. So the difference between these different lengths of integers is just how big do we need the integer to be. So an 8-bit integer, let's say, that can only represent, actually say it's an 8-bit unsigned. Let's say unsigned for a second. That can represent 0 to 255 because that's the biggest number you can represent with 8 bits. But a 16-bit integer can go from 0, like an unsigned integer can go from 0 to 64K, which is about 65,000 and thereabouts. So it's much bigger. So the more bits you use, the bigger the number representation can be. The most common thing to do is just to declare it as an int and leave it to the compiler to figure out. But if you happen to know the magnitude of the numbers that you want, you can control that by specifying what size integer you want. Now, integers also have a set of operators, binary operators I'm showing right here. They're also unary operators, but these are the binary ones. You've seen these in every language, plus, minus, times, all the arithmetic, shift, modulo. Comparison operators, so equal is a comparison, equality comparison. Exclamation equal, that's a not equal. Greater than, less than, so forth. There are Boolean operators, so and, or. And then bitwise operators, where it does Boolean operations per bit inside whatever the integer is. So you can see those too. But these are common to all, not all, but all standard languages have the same set of operators that you can operate on integers with. So we talked about integers. Now let's talk about type conversions a little bit before we go on to the next basic types. There are cases where you need to convert a number or a value from one type to another type. And for that, you use a type conversion. Now, these conversions are not always possible, okay? You can't necessarily do those conversions, but when they exist, when you can do them, here's how you do them. Let's say, for instance, you got some integers of different lengths. So I've got variable x, it's a 32-bit integer, and variable y, it's a 16-bit integer. And I want to say x equals y. I want to assign one to the other. I want to do some operations with them together. That, as shown, would actually fail. The reason why it would fail is because these two integers, they're actually two different types of integers. So the compiler sees them as two different types. Int32 is a different type than int16, so it'll throw an error when you try to set one to the other. Because when you assign like that, the thing on the left-hand side and the right-hand side, they have to be the same type. And it sees them, even though they're both integers, the fact they're different length means they're different types, and it throws an error. So in order to do this, you've got to convert one to the other. So for instance, you might say, let me take that y, which is an int16, and convert it to an int32, and then assign x to that, and then that would work. So the way you do type conversions like that is you use this t operation, where t is the type, the name of the type. So if I want to convert y, int16, into an int32, I just use this built-in function int32, right? And that will take whatever its argument is and try to convert it into an int32. So x equals int32y. That's what it would do. It would take y, which is int16, convert it to int32. Now this is a conversion that is possible. All it has to do is it sign extends the y integer. So the y value, you don't want to change y's value. It's equal to 2, right? So y is a 16-bit version of 2. And they want to make it into a 32-bit version, so what it's going to do is take the sign bit and just extend it. So if the sign bit's a 0, meaning it's a positive value, it just puts 16 0 bits in the high bits, gives you a 32-bit number, which is equivalent, also a 32-bit representation of 2, says that's equal to that. So this is a type of conversion that's possible, so it's easy to do, so you just use this int32 function to do it. Note that there are other type conversions that you can't do so easily, and it will fail on those, but some of them are possible, like this one. So another type, besides integers, are floating points. So floating points, they're basically real numbers, right? Now, depending on how many bits long the floating point is, like say you got float 32, that's going to give you approximately 6 decimal bit digits of precision, okay? Float 64 is going to give you approximately 15 decimal digits of precision. So you figure out how many bits you want to use, how big you want it to be based on how much precision you need. And often it tends to be, you want to go longer than shorter, right? Because precision errors are a common problem in floating point arithmetic. So you want to use more precision. The more precision is probably the better. Of course, there's a space issue, right? You use more memory if you make them longer. And also performance changes, right? But still, you don't want to, precision errors are an issue sometimes. So you can express floating point numbers with decimals or in scientific notation. So we can see 2 var x is float 64, 123.45, right? That's a decimal. It'll make it a floating point representation. Also, you can represent the same thing scientifically with this e as the exponent, right, for the 10. So this is base 10, so e2 means 10 to the 2. Also, you can represent complex numbers. If you want to, they have complex numbers. So if you remember complex numbers from high school or wherever you learned it, you got the real part and the imaginary part. This is how you create a complex number. You use this complex function. It creates you give it 2 arguments. The first number is the real. The second number is the imaginary. So 2 plus 3i would be that complex number if you're using complex. All right, so first we're going to talk about strings. In order to talk about strings, we need to talk about ASCII code and Unicode. So strings are going to be sequences of bytes. We'll see that in the next slide. But each individual element, each byte in a string, strings are made to represent different characters that you see, okay? So often strings are made for printing. They don't have to be for printing, but they're often made to represent printed things. So for instance, hello world, the string hello world, right? That's something that's meant to be printed and seen by a user. So now each one of these characters that you want to store in a string, each character has to be coded according to a standardized code. ASCII was basically the first accepted one. American Standard Code for Information Exchange, and it's just a character coding. So each character that you want to represent is represented with an 8-bit code. So, for instance, a capital A, right? A capital A in ASCII is the number 41 in hexadecimal. Okay, I just know that off the top of my head. It's a common code, but it's 41 in hexadecimal. So that's an 8-bit code. So ASCII is an 8-bit long code, which means it can maximum represent 256 possible characters. Really does 128 because one of the bits is used for something else. So that's not a lot of characters. So an 8-bit code is sufficient for English because there aren't that many letters in the alphabet. But once you start incorporating other characters that you need to include, so for instance, Chinese is a good example because there are a lot of characters in Chinese, right? You can't use an 8-bit code and hope to represent Chinese. So once you start trying to look at all these different character sets in different languages and different characters that maybe even aren't part of languages, but things that you want to represent anyway, that you want to show and have appear on the screen, you need a lot more than 8 bits. So that's what Unicode is for. Unicode is a character code that is a 32-bit long code. And so you can represent 2 to the 32, which is a lot bigger. 2 gig, I think. So it's a lot bigger. So that's a lot of characters. Now, UTF-8 is sort of a subset of Unicode. It's a variable length code. So it can be 8 bits, but it can go up to 32 bits. And the first set of codes in UTF-8 match ASCII. Right, so all the ASCII code values are the same as their UTF-8 values. So, for instance, capital A, it's in hexadecimal, it's a 41 in ASCII. It's also a 41 in UTF-8. Right? Now, UTF-8 also includes a lot of other codes, like for instance Chinese characters, right? And those aren't in the first 128, right? They're outside of that. They require more bytes. You can't just use a 8-bit code to represent those, so maybe those are 16 bits or 32 bits. So UTF-8 is a variable length code, but it can carry, it represents a lot more characters than you can represent with ASCII. Now, the default in Go is UTF-8. And in UTF-8, or Unicode, code point is a term for a Unicode character. Okay, so there can be up to 2 to the 32 code points, right? And in Go, they call a code point a rune. So rune is just a term for a code point. So the character, the capital A character, it has a rune which is represented with OX41, right? In hexadecimal, it's a 41. That you call that its rune. Okay, now to strings. Now strings are arbitrary sequences of bytes represented in UTF-8. So each byte is a rune represented as a UTF-8 code point. So these strings, they're read-only. You can't modify a string. You can make a new string that is a modified version of an existing string, but you can't modify an existing string. Often meant to be printed or displayed to a user. A string literal is just a string that's notated with double quotes. So for instance, if I say x colon equals hi there, that's a string literal, right? And that's a sequence of bytes. Each one of those bytes, each one of those characters, H, I, space, T, H, E, R, E. Each one of those is going to be represented as a rune, a UTF-8 code point. And they're put together in an array of those. We'll cover arrays soon, but an array of those is going to be a string. So we've already talked about strings. Strings are a common construct. You see them in every programming language. And strings are made of Unicode runes. They're basically arrays of runes. So there's a package called the Unicode package, which provides a set of functions that actually evaluate the properties of the different runes inside the strings. And it's useful if you're doing, if you've ever done parsing. You want to parse some string right out of a file, or out of a maybe somebody typed it in directly as user input, and you want to evaluate that string. When you're doing parsing, you need functions like these. So there are a long set of functions that the Unicode package provides to evaluate the runes. Some of them here are is digit, tells you if the rune is a digit, a numerical digit. Is space, is a space character. Is letter, if the letter is lower or lowercase. Is punctuation, is punct. So and these are all binary, Boolean, right? So they return true or false depending on if the rune is what it's saying to be, if it's a digit or if it's space or so on. There are also a set of other functions that perform conversions. So some of these conversions are possible. For instance, to upper and to lower. You can take a lowercase rune, turn it into an uppercase rune, right? And vice versa. So they provide functions for that. So they take a rune like to upper, it takes a rune which is a lowercase and returns a rune which is an uppercase, and so on. So Unicode package is useful for that. But there are other packages that are also involved in manipulating strings. There's the strings package. So the strings package, the functions that it provides are things to directly not look at the individual runes generally, but look at the whole string. So there are a set of search functions that are provided inside the strings package. These are common functions that you see in lots of different languages also. So for instance, first one would be compare. Compare A, B, you give it two strings, and it compares to see if they're equal. And actually, this compare function, it returns a -1. It returns 0 if they're equal. Returns a -1 if A is less than B, meaning earlier than it in alphanumeric order. And it returns a +1 if A is greater than B, so if A is later than B in alphanumeric order. So the compare contains, so you give S a string and then a substring. If that substring is contained inside S, it returns true, otherwise false. Has prefix, so you give it a string S and a prefix, and it returns true if that prefix is if S starts with the prefix. And index S, and you give it a substring. What that does is a search. It searches for the substring inside S, and it returns you the index of where the first instance of that substring can be found inside S, if it can be found. So this is the strings package. Now the strings package also provides a set of functions that manipulate strings. Now when I say manipulate, you can't change a string. A string is immutable. But there are a lot of functions that take an existing string and return a new string that is modified in some useful way. So first one would be replace. With replace, you basically take a string and it allows you to replace instances whenever it finds an occurrence of old, it replaces it by an occurrence of new. So these are all strings. So there's a big string S, there's a substring old and another substring new. It replaces instances of old with instances of new and returns you a new string. So S, the original string, is not actually changed. It returns you a new string with the replacements performed. To lower, to upper. So this will take the whole string and change it to lowercase or uppercase. Return, I keep saying change. It does not change the string. It returns a new string that is modified. Also, trim space is useful. That gets rid of leading and trailing white space from a string. So you get this a lot when you're reading from a file, let's say, and maybe the tokens on the file are separated by spaces. So if you just read directly from the file, you'll also read these spaces in, but you don't need the spaces. You just need the token. So you may call trim space to get rid of the spaces. Another package that has a lot of useful functions for strings is the string convert package. So generally, this provides a set of functions for converting strings from different basic data types, to and from different basic data types. So some of the big ones, A to I, as ASCII to integer is what it stands for. And it converts a string to an integer if that string represents an integer. So let's say you're reading from a file, you're reading a string from a file, and this string is a number 123. Now, when you read that, and you read that as a string, you can't do math on a string, right? You can't take that 123 and add 1 to it because it's a string type, it's not an int type. So you need to read that string in and then convert it to an int, and then you can do math on it. So you would use A to I to do a thing like that, and I to A does the reverse. It takes converts an int into a string, an equivalent string. Then format float basically does a similar thing for floats. So it converts a floating point number into a string representation of that floating point number, and then parse float does the opposite, converts a string to a floating point number. So a string, so if you have the string 123.45 as a string, it'll convert that to a floating point number that you can actually do math on. So let's talk a little bit about a constant. So a constant is pretty obvious what a constant is. It's an expression whose value is known at compile time, right? So you know it and it never changes. So you can just basically declare a variable to be a certain value, and it holds that value for all the time, as long as the program is running. The type is inferred from the right-hand side of the assignment. So for instance, here we got we say const x equals 1.3. So that's going to set x to the value 1.3, and you can the compiler looks at 1.3, sees that that's a floating point, and so x becomes a floating point. So it infers from the right-hand side of the assignment what the type of the variable needs to be, and it is held constant, can't be changed. You can assign many at once. So constant, we know y equals 4, z equals high, right? You can give a long list if you want to. So that's what a constant is. Now iota is a function used to generate constants. It's sort of interesting. So it generates a set of related but distinct constants. So when do you use this? You use this when you have to represent some property or some property that has several different distinct possible values. So this is also known as one hot. So if you know basically if you have a variable and you know it's going to be one hot coded, right? This variable can have one of 5 values, let's say. And so you want each one of these 5 values to be a distinct constant. Right? Now, in a situation like this, and just examples of such things, days of the week, right? You got 7 days of the week, and you want each day of the week, if you want to define a constant for each day of the week, Monday, Tuesday, Wednesday, you want them all to be constants which are different, and you don't particularly care what the value of the constant is, as long as Monday is different from Tuesday, which is different from Wednesday. Right? Months of the year is the same thing, right? So key thing about these constants is when you use iota to generate these constants, the constants need to be different, but the actual value of the constants is not important. So if I have Monday, Tuesday, Wednesday as my constants, I don't care if Monday is 500 or 5,000 or 2 or something, as long as Monday is not the same as Tuesday, which is not the same as Wednesday, right? So that's the case where you can use iota. If that's the case, you need to represent some set of constants, be all different values. You don't care exactly what the value is, but as long as they are distinct constants, then you can use iota. And this is essentially just like an enumerated type in other languages, like in C or something like that. It's the same idea. So they give you a nice little shorthand for defining these set of constants. So here's a little example of how you might define something using iota. Say I want to define some grades. So I make a type called grades. I make it an int. I want to represent my grades as integers. And I want to have these 5 grades, A, B, C, D, and F. And I know that I want A, B, C, D, and F to be all different grades, right? So they should be represented by different integers. But I don't particularly care what integers they're represented by. I just want A to be something different than B and C and D and F. So I declare the constants, A, B, C, D, and F, and the first one, I say A, give the type grades, right, which is actually an int. It's an alias for int. A grades equals iota. I say that on the first constant definition. Then for B, C, D, and F, I don't have to repeat that, right? As you can see, I just say B, C, D, and F. I don't give the type. I don't say iota. None of that. They just do it on the top. And what will happen is automatically iota will assign a value to the first constant, and then it'll assign a different one to the next one, a different one to the next, and so on. And actually what it does, what the implementation does is that it starts at 1. So A would be 1, B would be 2, C would be 3. But you should not depend on that, right? That's not, so you don't know, the idea behind using iota is that you don't care what the actual values of the constants are. You just want the constant values to be different from one another. So it happens that the current implementation starts off at 1 in increments, but you can't guarantee that in the future maybe that's going to be changed, right? Just all you know about iota is that they're going to be different. So control flow describes the order in which statements are executed inside a program. Now, basic control flow, the most basic control flow is just executing one statement at a time, one after the other, right? Procedural control flow, just top down. Now, the control flow changes for a lot of reasons, but the first reason why control flow changes is because the programmer inserts control flow structures into their code, which changes the sequence in which statements are executed. So the main control flow structure, the first one, is an if statement. Basically, with an if statement, you can conditionally execute certain sequences of code. So if this condition is true, then you execute sequences of code. If not, then you don't. Right? And this, what we're showing here is the most straightforward if statement without an else clause. You can also have an else clause, but let's start with the basic one first. So the structure is just if condition. You write some condition in there, x greater than 5, something like that. And this condition has to evaluate to a Boolean, right? If that condition is true, then whatever's inside the curly brackets, labeled consequent there, that's executed. And you can have any number of statements inside there, and that'll be executed if the condition evaluates to true. So this changes control flow because instead of just definitely executing the next statement one after the other, it checks this condition. If the condition is false, then that consequent, those statements in the consequent are not executed at all. And so we can see at the bottom, we got if x greater than 5, then it prints it performs a print statement, right? And if it's not, then it just skips that entirely. Now this if statement, this is a very vanilla if statement. You can also have an else clause after that, right? So if the condition is true, it executes what's inside the curly brackets. Then you can have a next clause, the else clause. It would execute whatever is inside the next set of curly brackets, the next block for the else, right? We didn't include one here, but this is a straightforward extension, and you see this in every major language. So for loops, they're another form of control flow statement. Again, so for loops, what they do, they basically they're loops. So the control flow, rather than just going top down, when you hit the bottom of the loop, you come back to the top of the loop. And you do it again and again until a certain condition is met or not met. So that's how they alter control flow. It's just, and these are extremely common in programming using loops. So they just iterate over a block of code as long as the condition is true. Now, there are several forms of for statements. We're looking at one right here. Probably the most common form. You see it similarly in C and things like this. If you look at the keyword for, right after that, there are three statements really. There's the initialization statement, init, there's a condition, and there's the update, and separated by semicolons. So the init is executed once at the beginning of the loop. So the first time you hit the for loop, it executes the init just to initialize things right at the top. Then the next block, that condition, that is checked on each iteration. So at the beginning of each iteration, that condition is checked. If it has to result, it has to be an expression that results to a Boolean. If that condition is true, then it executes all the statements inside the loop. Otherwise, it doesn't. Otherwise, it's done with the loop and it continues past the loop. So that condition is a termination condition. It determines when you stop executing this loop, because as soon as that condition is not true, you skip the loop and you're done. Now the update, that third block there, the update is what is executed at the end of each iteration, and it's used to update some element of the state. So a very common way in which you use this is you'll have some index variable for I equals 0. Maybe you start off with I equals 0, and you want to do this, iterate through this 10 times. So the condition might say I less than 10. And then the update would be I plus plus, or I equals I plus 1. Right? And then every pass through, it updates that I value, that element of the state. So, and one thing about these for loops is, unless you want an infinite for loop, which you typically do not want, you got to make sure that condition is at some point false, right? Because if the condition is always true, then you never leave the loop. So one of the ways, the most common way to make sure that condition is always false is to make sure that update changes the state in such a way that eventually the updates cause the condition to be false. So for instance, if I say I is equal to 0, I start off at equal to 0, and my update is I equals I plus 1, then eventually I will be greater than 10. Will be greater than 10. So the update guarantees that the condition is eventually false and that you eventually drop out of the loop. So here are some forms of for loops. These are basically the three most common forms of a for loop. Top one is what we've already seen, right? You got the initialization, you got the condition, and you got the update. The next one, if you look at the for keyword, there's only the condition check after it, right? No initialization, no update. You don't have to have those. Now, instead, what we did here to make it equivalent to the for loop before, we had to put the initialization before the for loop. That's another way of doing it. And the update is now built into the for loop. So if you look, there's an I++ inside the loop, right? So it's actually inside the for's block instead of, as you have in the first form, where you actually put it in there right after the keyword. But it's another way you can define a for, which is really just like a while loop inside another language. And then the last form is just an infinite loop. It has nothing after the for loop. It just is an infinite loop, which is not typically what we're going to be doing. You do that maybe in an embedded system, but it's not common to do in a regular program. You usually don't want an infinite loop. All right, so another type of control flow is a switch. Switch is paired with case, right? So a switch is a multi-way if statement. So you often get situations where you want to say, if this is true, you do this. If this is true, you do that. If this is true, you do that. Sort of, you do one of a set of cases. Sort of an else if else if is another way to write this type of thing. So a switch is like there's a set of cases, and only one of them is going to be executed, whichever one matches. So the switch typically contains a tag, which is a variable to be checked, right? So maybe I say switch x. So that's the variable I'm going to check. Then each case is associated with some constant value that x is compared to, that the tag is compared to. So tag is compared to the constant defined right after the case keyword, and then whichever case's constant matches the value of x, that's the case that's executed, and none of the rest are. So in this example, you can see we got switch x. Inside you got two cases, case 1, case 2. So if x is a 1, it'll execute case 1. If x is a 2, it'll execute case 2. And then the bottom one is default. Default is executed if none of the cases are hit. So it's an optional thing. You don't have to have a default, but you can have a default. So if it falls through, it'll end up executing something. So this is typical form for a case. And one thing to note, just if you're used to C, in comparison to C, the case automatically breaks at the end of the case. So in C, if you were to execute case 1, say x was equal to 1, you hit case 1, you execute case 1, it would also fall through and execute case 2, right? That's what C would do, unless you put a break statement in there at the end of case 1, right? After the format.printf, you put a break statement, then it would skip the other case in the default. In Switch and Golang, you don't have to do that. It just automatically breaks, which is a good thing. To continue with the control flow, we were looking at a switch. Let's talk about a tagless switch. This is a variant on the regular switch. So normal switches, they have a tag, right? Switch X, let's say, and that's the tag, that X, and that's a variable that's going to be compared to constants that are right after the cases, right? So case 1, case 2, case 3, X is compared to those constants 1, 2, and 3. So sometimes that's not what you want. Sometimes you can have a switch without a tag. And when you do that, then what happens is the case that actually gets executed is the first case whose expression is true. So what I mean by this is when you don't have a tag in the switch, then each case is going to have, instead of having a constant after it, will have some expression that resolves to a Boolean, true or false. And if that Boolean is true, then that's the case that's executed. And it'll execute the first case whose condition is actually true. So here's an example of that. In this case, we have a switch. There's no variable, no tag, right? And we just have these cases, 2 cases plus a default. So case X greater than 1, case X less than -1, and then default. So in this situation, since there's no tag, it just looks to the right of the case keyword, looks at the condition X greater than 1, evaluates that. If it's true, then that's the case that gets executed, and we're done to the switch. If it's false, it goes and checks the next case to see if its condition is true. And so on until you're done with all your cases, and then if none of them happen, then the default is executed if you've included a default. So that's a tagless switch, and you can use that as well. Instead of if, else if, you would use a switch like this, tagless switch. Break and continue are also control flow instructions. Sometimes they're considered bad form, but they definitely exist and they're used. So break and continue are for loops. So a break exits the containing loop. So say you're inside a loop, and that loop, so in this case, we got a for loop. And I equals 0, I less than 10, and there's an I++ inside the loop. So this is supposed to happen, whatever this is supposed to iterate through 10 times, conceivably. But notice inside the loop, it says if x equal 5, then break. So if it hits that break, and it will in this case, when it hits that break, it will exit the loop. So this thing will only execute for I equals 0, 1, 2, 3, 4, and 5. It'll go into the loop, and it'll hit the break on the 5th pass through the loop. So it won't finish the loop. So break just jumps out of whatever the containing loop is and quits the loop. Now continue, on the other hand, it's also used in loops. It doesn't quit you out of the loop. It just skips the current iteration of the loop. So if we look at the continue example, same code, except instead of a break, it calls a continue. If I equal 5, then it calls continue. So in this case, without that if statement and that continue, it would execute this loop 10 times, right? Because I starts at 0, it goes up to the condition is I less than 10, so it would execute 10 times. But for this loop, it says if I equal 5, continue. So that one iteration where I is equal to 5, it will continue through that. It'll continue and just jump right past that iteration of the loop. So it won't. So it'll still, the code will still, the loop will execute, but it won't execute as many times. It'll skip one iteration of the loop. So scan is a function to read a user's input. This isn't a control flow function, but we need to hit this because reading user input is something that you're going to use in the code examples that you write. It's sort of a common thing to do. You want to read input that a user types into the keyboard. So this is in the format package. What scan does is it takes a pointer as an argument. So what you do is you make a pointer to some value that you expect a user to type in. So if the user is going to type in an integer, you would make an integer and you would pass a pointer to that integer to the scan function. You'd call scan, and when you execute the scan function, it blocks, the program waits until a user types in something and hits enter. And when they hit enter, the scan function will take whatever they typed in and will place it wherever the pointer is pointing. Okay, so it will take what they typed in and put it into, say, an integer. If you pass a pointer to an integer, it will take it, turn to an integer, point it in, put it into that integer. So, and what it returns is the number of scanned items. It returns actually two things. The number of scanned items, the number of tokens that a person typed in. So space-separated tokens, that's returned. Also an error. The second thing that's returned is an error. If there's an error, it'll return something other than nil. If there's no error, it'll just return nil for that error. But if there's an error, it'll return an error code, and we could investigate that. So we can look at this example code. Let's say we make a variable applenum, and it's an integer. Then we print out number of apples, question, expecting the user to type in how many apples. So we expect them to type in some integer, 5, let's say, right? So the next line, it executes the scan function. The code will actually stop. The code will stop running there and wait until the user types in something and hits enter. So say the user types in a 5, hits enter. Now notice that the argument to scan, the argument passed, is ampersand applenum, which means the address of the applenum variable. So when the user types in 5, and hits enter, that scan function takes that number 5, puts it into the applenum variable. So on the next line, when I say printf applenum, it'll print 5 or whatever integer they typed in. Welcome to Module 3. Now we're talking about composite data types. So composite data types are data types that aggregate other data types together. So they bring together lots of different data types. Specifically, we're going to be talking about arrays, slices, maps, and structs. Composite data types are essential for complicated code, for real code, because simple data types, basic data types, aren't enough to describe the complex concepts that you're going to need to refer to in big pieces of code. So you need to aggregate them. Maybe you have strings here, integers there, you merge them all into one thing that describes whatever the concepts are that you're referring to in your particular application. And once you're done with this, you'll be able to use more complicated composite data types inside your Go code. So now we're moving on to composite data types. Composite data types are beyond the basic data types. They're data types that put together, that aggregate other data types. So unlike a string is just a string. Actually, even a string you can think of. Actually, a string is a sort of a special case because you could think of it as aggregating these different bytes. So a string is somewhat of, actually, now that I think about it, a string sort of is a composite data type. But we're going to talk more generally about arrays right now. So an array in general is just where you take a bunch of a fixed length series of elements of a chosen type. So you can make an array of bytes, you can make an array of integers, an array of floats, and so on. But it's fixed length. That's a key thing about arrays. They are fixed length. It is known at compile time how big they're going to be. So the compiler can tell how much space and memory it needs to allocate for these. And just in general, let me say that these composite data types are important. That is, in any kind of complicated program, you're going to need to use composite data types. It's not enough to use the fundamental data types. You need to bring together different data types and group them and aggregate them into some kind of a composite data type. So you have different array elements, right? Each one is some chosen type. Maybe it's an integer array. You've got a set of each array element would be an integer. Elements of each of the array, each element is indexed by using subscript notation, so square brackets. You put the index right in the middle of the square brackets. So we're going to have an example here, but this is similar notation to what you see in lots of different languages. Indices start at 0, because we're computer science, we start counting at 0, not 1. Elements are initialized to a 0 value, and actually this is not always the case in other languages. Say in C, you make an array, that array is not initialized at all, right? Unless you actually write code to initialize it. When you create it, it's not initialized. But in Golang, the array is initialized to 0 value. And when I say 0 value, I mean the 0 value of the type that the array is composed of. So if it's integers, the 0 value is just 0. If it's strings, the 0 value is empty string, right? So in this example, we're showing how you can declare an array. So you see at the top var x, and then in brackets 5, int. And the fact that it has the brackets 5 tells you this is supposed to be an array of 5 integers. So that's how you declare an array, and that would be initialized to zeros by default. Then next line, I refer to a particular element, x0, x bracket 0, right? So I'm looking at the 0th element, and I'm setting that equal to 2. So now I've changed that element equal to 2. And then the next line I'm doing a printf, so do a printf x of bracket 1. And since bracket 1, I didn't actually explicitly initialize that, it would have been initialized to 0, so that'll print to 0. So that's an array, and you've seen that in other languages most likely. An array literal is a predefined set of values that go into that make up an array. So you use this to initialize arrays if you want to. So for instance here, we say var x bracket 5 int. So it's an array of 5 integers. We say equals, and we say square bracket 5, and we give, within the curly brackets, there are actually 5 integers, right? So that's actually a way of initializing the array to a set of values, to an array of 5 integers. So that array of 5 integers that's inside the curly brackets, that's actually called an array literal, and we're defining x to be equal to that array literal. The length of the literal has to be the same as the length of the array. So if you declare x to be 5, you better have 5 literals inside the array literal. Now then there's this operation, that dot dot dot. That's actually a keyword. So dot 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 is used to express the size. You can use dot 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 to express the size of an array literal. You can do that because basically if you have an array literal and inside the curly brackets you have 4 elements in there, then it's clear that you want this array literal to be size 4, right? You don't have to say explicitly 4, so you can just put a dot 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 in there, and it will infer the size of the array from the number of elements inside the array literal. So in this example, x colon equals, in brackets we have dot dot dot. We don't specify explicitly what the size is. It says int 1, 2, 3, 4. So it says 4 elements in there. Clearly you want x to be size 4. The most common programming operation that you do to arrays is to iterate through the array. You look through each element of the array and you do something with the element of the array. Maybe you add it to a sum, or you check to see if it's greater than 5 or something like that. But it is extremely common in programming to iterate through an array and check out each element in the array. So the way you do that in Golang is with a for loop. So you can see in the code here, we've got some sample array, 1, 2, 3, right? It's just 3 elements in it, 1, 2, 3. Now we want to iterate through this array. Maybe we want to print out each element of the array. So we make a for loop. Now notice that I have highlighted in there that range keyword, right? To the right of the range keyword is the name of the array that we want to iterate through. So range x. To the left, we say for I comma v. We got 2 variables here, I and v. I is the index of the array element that we're looking through in this particular pass, and v is going to be bound to the value of the array element that we're looking at in this pass. So the idea here is that in this loop, if you look inside the curly brackets, there's a print statement. That print statement is going to get iterated once each pass through the loop. So every pass through the loop, I and v are bound to different values. I is the index of the element that we're looking at, and v is the value. So in this case, with this array, the first pass through the loop, I is going to be 0, next pass is going to be 1, next pass is going to be 2, right? It'll increment each time. And v is going to be the ith value in the array. So the first pass through, when I is equal to 0, v is going to be equal to 1, because the first element in that array is the number 1. So the 0th element is the number 1. Then in the next pass, I is going to be 1, and v is going to be 2, because the first element, from 0, 1, first element in that count, is the value 2, and so on. And all this loop does is very simple. It just prints out the I and the v together. But that's the idea. This allows me to iterate through the array. So I and v get bound to an index and a value inside this array on each pass. And so inside the loop, inside the curly brackets of the loop, we can do whatever we want to that value v, right, and to that index I. So a slice is a data type that you don't see in a lot of other languages. A slice is a really useful data type. So a lot of times actually slices are used instead of arrays because they're flexible. You can change their size. You can increase them in size. So let's talk about slices and how they define. Basically, a slice is a window on an underlying array. So for every slice, there's got to be some underlying array that is the basis for the slice. The slice is just a window of it, a piece of it. So you've got a long array of 100 elements. The slice is just, maybe it's just 3, 4, and 5 or something like that, or elements, or 5, 6, 7, 8, 9, something like that. That's basically what a slice is. A window on a larger, possibly larger array. It doesn't have to be larger. The array can be the same size as the slice, right? Then the slice is just looking at the entire array, but the array can be much bigger than the slice, and the slice can be just a smaller window on it. So that's essentially what a slice is. So slices have they can have variable size up to the size of the array. This is one thing that's really nice about slices. You can increase the size of a slice. See, an array is a fixed size thing. So let's say I have an array of size 100, and I have a slice of size 10, which on that array, and it's the first 10. I can increase the size of the slice to 20 and just look at the next 10 elements of the array. And then I can increase it to 30 and include the next 10 elements of the array. So slices, you can increase the size of the slice where you can't do that to an array. So that's a good feature of slices. Now, every slice has basically three properties. One is the pointer, okay? That indicates the start of the slice. So every slice, since it's a window on an array, it has to point to some element of the array that is the first element that is included in the slice. That's the pointer. The next thing in a slice, the next property of a slice is its length. It's the number of elements in the slice, because they all have a length. The third is the capacity. So the capacity is the maximum number of elements in the slice. Now that's defined by looking at the pointer, which is the beginning of the slice, and looking at the difference between that and the size and the distance to the end of the whole array. Because a slice, its size can be increased up to the size of the whole, up to the end of the array. So for instance, say you got an array of size 100, you got a slice of size 10. You can increase that slice's size. Say the slice starts right at the beginning of the array. You can increase the slice's size all the way to 100 if you want to. So it has a capacity of 100. But say you got an array of size 100, but this slice starts at array index 10, right? Then it can only be increased to size 90 because by then you reach the end of the array. So the capacity of that slice is smaller. So let's look at an example to see what I mean by these things. Slice example. So first we start with the underlying array. We've got this array. We define it with this literal, it's got, let's see, A, B, C, D, E, F, and G. That's the array. Array of strings. Now, then we define two slices on this with that array as the underlying array, S1 and S2. Now, here's how we define these slices. We use this bracket notation and we use the colons inside the brackets to define the beginning and the end of the slice. So, if you look at S1, S1 colon equals array ARR, bracket 1 colon 3. The 1 is the pointer to the first element of the array that is inside the slice. And the 3 is the index just after the end of the slice. So that slice, S1, it includes array elements 1 and 2, not 3. So the second number after the colon is just after the end. Now if we look at S2, that's 2 colon 5, right? So S2 starts at 2 and includes 3 and 4, does not include 5. So we can see this in, we can see the picture down here at the bottom. You got the array in blue, the whole array, and it has the A, B, C, D, E, F, G. Then in red, I've highlighted S1 and S2. So S1, it includes index 1 and 2, right? Because 1 colon 3, so 3 is just past 1 past the end. And S2 includes 2, 3, and 4. And notice that these two slices overlap, and that's okay. If you look at S1 and S2, they both include array index 2. Right, so, and that's fine. Array slices can overlap and refer to the same elements inside the underlying array. All right, so the length and capacity. So there are two functions, len and cap, which return the length and capacity of a slice. So we got our array A1 here, and it's 3 elements long, A, B, C. Then we define a slice, SLI1 I'm calling it this time, and that is the array 0 colon 1. Okay, so that means that this slice includes array index 0, but not array index 1. So its length is actually 1, should be 1, right? It only has one element in it, array index 0. But, so if we, now in the next statement, we do the print statement. We print the length and the capacity. The length is 1, right? 0, and then 0 is the only thing that's actually in the slice. But its capacity is still 3 because it could be, its size could increase up to 3 if I increase the size of the slice to go all the way to the end of the array. Since the array has 3 elements in it, and we're starting the slice at the beginning at array index 0, we could go all the way through at array index 0, 1, and 2, and the length of the slice could be up to 3, so its capacity is 3. Now, accessing slices, or really referring to slices. So when you write to a slice, to an element in a slice, you are writing to the underlying array. And overlapping slices can refer to the same array elements. So you change one slice, you can change the underlying array, and you can change any other slice that also accesses that, also includes that array element. So here we got these, in this picture, we're showing this array. We got S1 and S2 are two different slices defined on it. Now see, in green, I circled that array element 2 with the string C in it, right? So that one is actually included in S1 and in S2. Now in S1, with respect to S1, that is the S1 colon bracket 1. It refers to that second element of the array, right? Because S1 0 would refer to the first element of the array because that's where S1 starts. So S1 bracket 1 refers to that C, that letter C. Now S2, that second element of the array is the first element in S2, so that's the same as S2 bracket 0. So these two print statements will print the same thing, the letter C, because S1 bracket 1 is the same as S2 bracket 0. They're both referring to the same element in the underlying array. Now, we talked about array literals. You can also have slice literals. They can be used to initialize a slice, just like an array literal can be used to initialize an array. Now remember that every slice has to have an underlying array. So when you initialize a slice, that means you're creating an array. You have to create the underlying array. And the slice just covers the entire array. So when you use a slice literal to define a slice, it actually creates an underlying array, and it creates a slice to reference the entire array. So the length and the capacity of the slice are the same, right? So the slice, if you do this, if you use a slice literal to create this array, the slice its pointer will point to the beginning of the array, and its length will be the length of the array, and its capacity will also be the length of the array. So the slice points to the entire array when you use a slice literal to define it in this way. So we can see that here, we're defining using a slice literal. SLI is defined as a slice literal, and it defines the underlying array. And you know that this is a slice literal because you can see where I say SLI colon equals brackets. Normally in the brackets you'd put the length if it was an array, or put 5 or 3 in this case, or you'd put at least ... to say this is an array. Its length should be inferred from the number of elements inside the curly brackets. But in this case, we didn't put anything in the brackets. So the compiler says, oh, this must be a slice. And what it does is it creates the underlying array, and then it makes the slice point to the whole array. So there's a function called make that can be used to make slices. And you can make other things with it too, but right now we're going to talk about making slices. And so the one way that we made a slice, the first way we talked about making a slice was just to make the underlying array and then make the slice after it. Also, you can initialize the slice directly with a slice literal. We talked about that. This is the third way. You make the slice directly, but you're not initializing with any particular values. So this is common. This is when it's a case like this where you want to use a slice because it has this variable size ability, and you don't care that there's an array in the back, right? But you want to initialize a slice to a particular size, so at least at the beginning. So one thing you can do is call make. There are two ways to call it. You can call it with 2 arguments or 3. If you call it with 2 arguments, the 2 arguments of the make are the first argument is the type. So the type of the objects that are going to be inside the slice. So if it's a slice of ints or slice of strings or something like that, that'd be the first argument, int, string. And then the second argument is going to be the length of the slice. Now when you use make to make a slice, the length is equal to the capacity because it makes the underlying array, and the array is exactly the same size as the slice. So the length and capacity are the same. So when you that is anyway when you use the 2 argument version of make. So you can see here SLI equals make. We say bracket int to tell the type, and then 10. So since I gave 2 arguments, it figures okay, length and capacity are the same. So the underlying array is the same as same size as the slice, and the slice points to the beginning, starts at the beginning of the underlying array. Now the 3 argument version of make, instead you specify the length and the capacity separately. So that means that the underlying array is actually bigger than the slice. So in this case, we got SLI equals make. First, we give the first argument the type, bracket int. Second argument is the length of the slice. The third argument is the size, the capacity, which is the size of the array. So in this case, our slice is size 10, but the array is size 15, so we can increase this slice up to size 15 if we want to. So there's an append function that can be used with slices, and it's used to increase the size of a slice. So if you want to add stuff onto the end of a slice and increase the size of the slice in doing so, you use the append function. Now note that this is a key advantage, right? Compared to regular arrays that you see in regular languages, you can't just add things to the end of an array and continually increase its size. But with a slice, you can. So it adds the append, it adds you can add one or more elements. In this case, we'll do one, but it adds the element to the end of the slice. And which means it inserts it into the underlying array. So it increases the slice up to the capacity of the underlying array. And it increases the size of the array if necessary. So if you reach the limits of the array size, it'll make a new underlying array that's bigger. So append never has to stop appending. You can continually append even beyond the size of the array. It'll just increase the size of the array. You don't want to do that. There's a time penalty for that, but it'll do that. So as an example, we make a slice. SLI, we call make. So its size, the size of the slice, the length of the slice is 0, but the length of the underlying array is 3. So then I want to put something into the slice. So the slice is empty, right? The size is 0. So I append the number 100 onto the slice. So I call append. I pass the first argument, I pass the slice, the name of the slice, and the second argument is 100, the number that I want to put into the slice. So it puts it in. In order to add that on, it has to increase the length of the slice. So now the slice's length would be increased to accommodate the new number that it put in there. So that's how you would use append in general. A hash table is a data structure used in a lot of different languages, and it's a very useful data structure. It allows you fast access to large bodies of data. A hash table generally contains key value pairs. So there are a lot of values inside this hash table, but each value is associated with a unique key. So for instance, maybe social security numbers and emails, right? So the social security number might be the unique key of the person, and so that might be the key, and then the value might be the email address of the person. So that's a pair, right? Key, unique key, and value. And the key has to be unique. That's actually completely important. Also, maybe like a GPS coordinates and address, right? So every address has a unique set of GPS coordinates associated with it. So GPS coordinates might be used as a key, and then the address might be, your house address, right? Which may or may not be unique, right? Where you live, there are a lot of different main streets in the world, and there can be a lot of different main streets. So that might not be unique, but the GPS coordinates have to be unique, or the key has to be unique, in this case, GPS coordinates. So a hash table is meant to store these key value pairs, and it is important that each key is unique. So a hash function is defined, and it's used to take a key and compute a slot in the hash table to insert the value according to the key. So you can think of a hash table as something like, I hate to say it, but think of it like a big array. It's got a lot of slots where you can put values in there, right? Now, which slot it puts the value in is based on the key. The hash function is used to process the key and generate the number of the slot that you want to insert the value into. So a hash function is a function that takes as its argument the key, and it returns the slot where you want to put the value. Now, by the way, this hash function, you never call this hash function explicitly. This is something that goes on behind the scenes inside the Go language. But just understand there is such a hash function that does this. So here's an example of what a hash table might look like. So at the top, we got this little table, a bunch of keys and values. So my keys are Joe, Jane, and Pat. They're all unique keys. They're strings. They're unique. And here's some values, X, Y, and Z. They're arbitrary, okay? So Joe is associated with X, Jane's associated with Y, Pat's associated with Z. And I want to put these three key value pairs into my hash table. So if you look at the bottom, you got on the right, you got this basically an array, right, of some size. And this is a small one, but this is just an example. So you got some array, And the values x, y, and z are all placed in different slots inside this structure. So and I just place them arbitrarily. Okay, y is in was it in location 1, and x is in location 3, z is in location 5. Right. So they're in some arbitrary location, some slots inside the structure. Now then over on the left, you can see the keys: Joe, Jane, and Pat. Now there in between there's this hash function, and the hash function, it takes the key and determines which slot it's going to place the corresponding value in. So I drew this with little lines. So if you look at Joe, there's a blue arrow that goes into the hash function and then points to location 3, slot 3. So Joe is associated with slot 3, which has the value x. And then Jane, the hash function will compute a 1 in this case. And so slot 1 has Jane's value y. And then likewise with Pat, Pat is associated through the hash function with slot 5, and you put its value z inside slot 5. So this is the idea behind a hash table. So the reason why this is good is something like an array or a slice, right? You can access things in constant time, but you don't have to use indices to access them. You can use arbitrary keys, right? As long as the keys are all unique and constant, then you can use the key. So normally if this were an array, if I wanted to access in entry 1, element 1, I'd have to say the name of the array and then brackets 1. In this case, I can say brackets Joe or bracket Jane or bracket Pat or something like that. Okay, so that's actually useful. The naming is useful for several reasons. One reason is it's easier for a programmer to remember Joe and Jane and Pat rather than arbitrary numbers, right? The numbers have no particular meaning with respect to the particular application you're writing, where Joe and Jane and Pat, they are people and they have some sort of a meaning in the mind of the programmer. So it makes it easier to code. So advantages. Advantages are faster lookup table than lists. So this is an advantage compared to like a list that you'd find in another language. It's faster lookup than list because in a list, it's linear time lookup. So that means if you want to find an element in a list, you have to start at the beginning of the list and go to the next and next and next and keep comparing until you find the one you want, find one that matches. That's linear time. The longer the list is, the longer it takes to find things in the list on average. Where this is constant time. It's much more like an array, right? You take the index, the key rather, you use the hash function, which takes some constant amount of time, and it gives you the index, and you go straight to that index. So it's a constant time lookup rather than linear time like you would find in a list. Now, another thing about it is that you can use arbitrary keys. So this is better than, say, slices or arrays where you would have to use integers. You can use arbitrary keys, and those keys can have some sort of a meaning to them. So disadvantages is that you may have what are called collisions inside your hash table. So collision is when two keys hash to the same slot. So Joe and Jane, if the hash function maps both of those to slot 2, then you have a collision. Then Joe's value and Jane's value both have to go into the same slot. Now, there are ways to handle these collisions, right? You can put them both in there and put them in a linked list or something like this, but when you get collisions, the speed gets a little slower, right? Because those collisions have to be handled in some way. So you don't have to worry about how they're handled. That's built into Go. But that can slow you down. But I'll say this, that collisions are rare because the hash function is made in such a way that collisions are very rare. Okay? So this is a possible disadvantage with collisions, but it's not likely to cause you many problems. So a map is Golang's implementation of a hash table. So a map is exactly a hash table. You can use the make function to create a map. So we have an example here. So first thing I'm doing is I'm declaring ID map as a variable, a map variable, right? So I say var ID map, and it's going to be a map. And notice that after the keyword map, I have in brackets I have the word string. That's the type of the key. And then after that, I have another type, and that's the type of the value, right? So the key and the value can be different types. Then line after that, first I'm declaring ID map to be a variable. Then I'm actually assigning it, pointing it to a map, making it an actual map, and I call make for that. So ID map equals make, and then parentheses, map string int. right? So it creates a map. Now, at first, this make is going to create an empty map, but it creates a map. Now, another way to define a map is you can create the map with a map literal. So you can initialize it with values, with key value pairs, rather. So I'm showing that down here. ID map colon equals map string int, and then in curly brackets I list a bunch of key value pairs separated, and the key and the value is separated by colons. So in this case it's just one pair, but you can have a comma separated list of key value pairs. In this case it's Joe colon 1, 2, 3. So Joe is the key, 1, 2, 3 is the value. So, and you can put any number of those. You can initialize it with any number of those key value pairs. Accessing maps. So how do you access the elements in a map? At first, actually, most of it is the same as the way you would access an array, except the index that you use, that you put in between the square brackets, that's actually the key. So if I want to read the value associated with the key Joe, I can say, in this case, I'm doing a print, format.println, ID map, and then in brackets I say Joe. I give the string Joe, and that will return the value associated with Joe, and it'll print that. I can also add a key value pair into the map, or change an existing one if it's there. So if I want to add some new key value pair, I could say ID map Jane. Maybe there's no key Jane in there right now. ID map Jane in brackets equals 456. So that puts a new key value pair in there. Now note that would also change a key value pair. So let's say there was already a key value pair in there. Jane was mapped to 6, 7, 8, right? So by saying ID map Jane 456, I'm getting rid of the old key value pair associated with Jane, and I'm putting a new one in there. So Jane is now associated with 456. Also, you can delete a key value pair from the map. So without overwriting it, you can just delete it completely by calling the delete function. So you call delete, you pass it, the first argument is the name of the map, so ID map. Second argument is the key that you want to delete. So in this case, Joe, and it'll eliminate that key value pair Joe, and Joe and whatever its value is, it'll eliminate that from the map. So there are also a few more map functions. One thing that you can do with maps is you can have a two-value assignment for a map. So for instance here, I'm saying ID comma P colon equals ID map Joe. Now, when I do that assignment, if I had just done a single value assignment, say I said ID colon equals ID map Joe, then ID would equal the value associated with Joe. In this case, I'm doing a two-value assignment. So the second value, ID comma P, that P is going to be a Boolean. It's going to be true if the key is present in the map. So there are cases where you're interested in knowing whether that key is in the map. Maybe you don't even care what the value is associated with Joe. You just want to know if Joe is in your map. So P will be true if that key, Joe in this case, is in the map, and it'll be false otherwise. There's also the length function. You can apply that to maps. And if you do, you say, like here, I'm saying I'm printing len of ID map. It'll tell you how many key value pairs are inside the map. Another thing that is very common to do is to iterate through an entire map, just like iterating through an array. Very common thing. You want to iterate through every key value pair. So what you do here is you're using basically a two-value assignment with the range keyword. So it's a for loop. So if you look at the for loop, you got the key, and then the value, key comma value, and then that colon equals range, right, on the ID map. So what that does is every pass through the for loop, key is going to be equal to the one key inside the ID map, and val is going to be equal to the corresponding value in the ID map. So in this way, every pass, every iteration through the for loop will use one key and one value pair. So key and value will be bound to a different key value pair for every iteration through the for loop, and you'll iterate through the for loop until you've gone through every key value pair inside the ID map. So a struct is another aggregate data type, another composite data type. It's an aggregate type, meaning it groups together objects of arbitrary data types into one object. And it's useful for a lot of things. Usually it's for organizational purposes. It really helps. So let's give an example, easiest way to talk about it. You got, let's say you want to make a struct. Struct is short for structure, by the way. And by the way, this is taken also straight from, say, C as structs too. So say I want to make a structure that describes a person struct. So say every person has certain features, a name, an address, and a phone number. So for every person, I want to represent these three different aspects of a person. So one option would be to have three separate variables. For every person, I'll have three separate variables, and the programmer has to remember that they're related. So maybe I have name one, and I might use naming for that. So I might say, well, name one, address one, phone one. I have three different values, right? And I put one after all of them, so I as a programmer can remember, okay, this is name one and address one and phone one. They must be related. They all have one after them, right? And then the next person I make, I'll call it name two, address two, phone two, and so on. So that's one way. And in that scenario, these three pieces of information, name, address, phone, they are related. They have to be, the programmer themselves has to remember that they're related. Okay? That this name is related to this address and this phone, where this other name is related to this address and this phone. Now, another way, probably better way to do this, is option 2, is to make a single struct that represents a person. And that struct, it aggregates all three variables. So this one object now contains a name, address, and phone number of one person. So they are related because they are in the same object. And so when you're accessing them, it is obvious that if you're accessing them from the same object, you know that they are related to the same person. So that's what a struct is for bringing together different variables that are related in the application and putting them together so that you as a programmer know that they are related and they are related to the same person or whatever the object is in the application that you're talking about. So here's an example of a struct. You've got, so we're defining a type, a struct type, and we're going to call it person. And this person has three fields, three pieces of information, a name, address, and phone number. So notice how I'm defining this struct type. It's called person. I give it its name. It's a person. And each one of these fields, name, address, and phone, has a type, name, string, address, string, phone, string. After that, once I define this type, I can define any number of persons, right? I can say var p1 is a person, var p2 is a person, and so on. And p1 in this case, it's going to have a name, address, and phone number all its own. So each property is called a field. So name's a field, address is a field, phone's a field. And p1 can have values for all of those fields that are unique from another variable, p2, which is a person, or p3. So I can have any number of persons in there. So if I want to access the fields of the structure, by access I mean read from them or write to them, change them, I use dot notation. This is not like with arrays. With arrays, you use the square brackets and use an index. You use dot notation here. So p1.name, if I want to assign that to Joe, I can say p1.name equals Joe. And that will assign the field, the name field of p1 to the string Joe. Also, I can read in the same way. I can say x equals p1.address. Right? And that will assign x to be the address of p1. So use dot notation rather than the brackets that you would use with arrays. Initializing structures. You can initialize them using the new function. One way to make a sort of an empty struct, it initializes all the fields to zero values. So like in this person structure, the values are all strings, right? So the zero value is going to be empty string. So I can say p1 colon equal new person, and it'll make a new person that's empty. This will zero it out. So the name, address, and phone number will all be empty string. Another way you can initialize the structure is you can initialize it with a struct literal. So if you want to give values to all the fields right when you create the person, and we're showing that here, p1 colon equals person. Then in parentheses, I'd give the struct name, the struct name and then struct value, right? So name colon Joe, comma, address colon a.st, right? A Street, and then comma, phone colon 123. Right? So in this case, I'm using a struct literal, and I'm making a new structure, but I'm also assigning all the fields to different values, Joe and A Street and 123. So I can do that too. Welcome to Module 4. We're talking about protocols and formats in this module. Standardized protocols and formats. So the idea here is that when you write code, it is very common to want to interact with other systems outside of your own code. And when I say interact, I mean trade data. You get past data to the other system, it just passes data back to you. This happens all the time. Maybe it's networked. You're communicating with some network server or something like that. Maybe you're just trading data files. You have a database and it's in a particular format. You want to give that to another piece of code, another system, or you want to accept a database format provided by something. So in order to do this type of communication and interaction between different systems, there are many standards that exist, standard communication protocols and standard data formats that exist that allow you to communicate with other systems. HTML, JSON, there are a ton of them, and we'll talk about some of these. And Golang has packages that allow you to interface with these standards. Not all of them, but all the big ones. So HTML, there's a package just for dealing with HTML. JSON, there's a package for that, and so on. So we're going to talk about some of these packages, and you'll be able to use them inside your code and communicate with other bigger systems. So an RFC is a request for comments. That's technically what it means. But what it really is a definition of a protocol or a format, a standard definition. Now, the reason why we're concerned with these, they're not part of Golang directly. But whenever you write a big program, you will, to do something, you're going to want to interact with other systems, other blocks of data somehow. I mean, it is extremely common. So for instance, maybe you want your program to read database files, and process them, right? So these database files, maybe they came from some other source, some data, maybe somebody inserted them on the web, added to a MySQL database, and you want to be able to read those files, right? So there's got to be some format that everybody agrees on that you can communicate through. So this is going to be in this particular format, and your code can process that format. Same thing goes for maybe it's a network protocol, right? So maybe your machine, maybe you want to do a client-server thing, right? So you want to make a web client, and your web client needs to talk to a server over the network. And in order to talk to a server, it's got to send messages that adhere to a particular protocol, so the server understands what it's getting. And then on the other end, on the receiving end, your program has to be able to understand the format, the protocol of the messages that it receives in return. Right? So whenever you make some kind of a bigger system and it needs to interact with other systems through data transfer, this data has to be formatted in a way that everybody understands it. So there are many of these formats and protocols that are well-defined and are standardized and used for communication and trading data between different systems. There are many, many of them. And RFCs are the name that are used for a lot of these standards. Now they're non-RFC based standards, but RFCs are sort of a broad swath of standards. So for instance, let's give you some examples. Take HTML, hypertext markup language. HTML is the language in which web pages are written. So it's a standardized language. Actually, it's RFC. I got the RFC number right there on the slide. And it's a standardized language so that all clients, all web browsers, they have to understand this language so they know how to render it on the screen and so on. So that's one of those languages that's standardized. And you can trade data between a client and a server, between a web client and web server, using this standard. Also URIs, right? These are also, it's an RFC too. URI stands for Uniform Resource Identifier. It's basically the addressing method used on the web, right? So you've heard of a URL, that's the type of URI. So there's a particular format in the way those are supposed to see, and that it's got to adhere to a particular format so that every client, every server can interpret the address. HTTP, that's a network protocol, web network protocol, defines the web. Hypertext Transfer Protocol, okay, and that's RFC 2616, and that describes how the messages should be transferred on the network. So what information should be included in each message and what the headers are, where the data should be, the content and so on, the length, stuff like this. That's all defined so that a client can talk to a server, a web browser can talk to a web server, something like that. So these are just a few of the protocols, of these standard protocols. that are defined by RFCs. And there are a lot more. And these protocols can be arbitrarily complicated, some of them, right? Some of them are simple, some of them are complicated. And so what happens in Golang, a language like Golang, they provide packages that help you to process these formats, a lot of these. Not all, but a lot. So there are packages for most of the important RFCs. There are packages already built that you can incorporate, you can import into your program. So, and these packages, they provide a set of functions that you use to encode data into whatever the protocol is, the format is, and also to decode, right? So if you're receiving something in a particular format from some other source, you need to decode that information into structures, maybe structures or maps or some kind of Golang objects, right? And encoding is the other direction, where you take some kind of Go objects and you convert them into this common protocol or format. So as an example, there's net/HTTP. That's for HTTP, Hypertext Transfer Protocol. And you have that package, and it provides a bunch of functions in there that allow you to make messages and send them. So for instance, I've got this example, http.get. That makes a get message. You pass it as an argument a web domain, and it will make a request to that domain for a web page. And it'll return the actual content of the web page for you, right? So there are a set of functions like that defined in this package that allow you to communicate over the web, right? And send, so if you want to make a web client or a web browser, web server, something like that, you would use a package like this. Another package, a more basic one, is the net package, and this is for TCP/IP and socket programming. This is sort of a long description, but TCP/IP basically define the internet. So internet, you can do web-based communication on the internet, but you can do all kinds of communication protocols on the internet. FTP, Secure Shell, there's a whole list. But all of them share in common this basic TCP/IP UDP stack. The set of protocols that they all have to adhere to. And so the net package gives you a set of functions that allow you to use that protocol. So for instance, this example here, net.dial TCP says, look, I want to make a TCP connection, and you give it the domain uci.edu:80 tells you the port number. You pass that, and it establishes a connection, an internet connection, TCP connection specifically, with uci.edu on that particular port, which happens to be a web port. But so there are a lot of these packages that are used to make it easy for you as a programmer to use these different protocols, communication protocols, and data formats that are commonly used by different systems. And it's just a very useful thing to have these packages and to use them, because when you don't have them, you have to do it from scratch. Meaning you have to, for instance, take HTTP. If I didn't have the HTTP package, I would have to understand everything about HTTP and make the packages on my own. I'd have to basically make the message format and my own. I have to write my own code to do that. Now, this is not impossible, but it is time consuming. Why do that when you can call http.get? It makes it a lot easier for you as a programmer. So JSON is one of these protocols. It's not a protocol, it's a data format. Commonly used data format across the world, and we're going to talk about that and the package associated with it. So JSON stands for JavaScript Object Notation. We are not programming in JavaScript, but JSON is bigger than JavaScript now. JSON is just widely accepted as a common way to represent structured data. It's RFC 7159. It's a format to capture structured data, and by structured data, I mean a set of attribute value pairs. So this is a natural for a struct or a map, right? Because if you remember structs, they have not keys, they don't call them keys. They have fields and values of the fields, right? So a field value pair could be an attribute value pair in JSON. Or a map has key value pairs, right? That's the same, that can easily be an attribute value pair. So these attribute value pairs in JSON sort of naturally, I shouldn't use the word map, they naturally correlate to structs and maps inside Golang. And now the keys and values, or rather attributes and values as they're called in JSON, they can be basic value types. So you can take Boolean, numbers, strings, arrays, objects, and they can be combined hierarchically. So it's easier if we see some examples of this. So let's take an example of let's start off with a Go structure. right? A Go struct, the person struct that we had before, right? So this person structure, I'm making P1. I'm saying P1's person with a name of Joe, address of A Street, and a phone number of 123. So that information, maybe if we want to transfer it to another machine somewhere else. Okay, we want to give it to somebody. So we want to take it from, right now we have it represented as a structure in Go. We want to represent it in this common JSON format so that somebody else, some other program, some other system somewhere can interpret that. So what we're showing below is the equivalent JSON object. So up above you see the struct as we would define it in Go. And in JSON, what it would look like as a JSON object is shown right there. And notice this is very similar to the structure, to what a struct looks like or what a map looks like. It's basically name colon Joe, address colon A Street, phone colon 123. Now, one thing to note is that the name, the field names, the attribute names, name, address, phone, they're in quotes, right? Which they weren't when we defined the Go structure. We didn't put them in quotes, so it's a little bit of a difference. But notice that it looks very similar to the struct, right? So that JSON object, we can take that and pass that on to some other machine, some other program, and if they can interpret JSON, then they can extract all the information that we were using in our program about this person. And this is, of course, one person, but I could have a database full of people, and I could just make a set of JSON objects, pass it to somebody, and they could read this database full of people. So this is just a sort of a simple example of JSON, but JSON is actually nice, and it's a good format. It's well accepted. So JSON as a format has several properties that are advantageous. One is that it's all Unicode. Okay, so any JSON object, once you convert something into JSON, it's going to be represented all as Unicode characters, which is good because Unicode is understandable by people. In fact, that leads to another thing. It's generally human readable. Right? It's a human could look at the JSON format and understand, for the most part, what it is. It might be slightly complicated, but it's readable by a human. Now, it's also a fairly compact representation. I say fairly compact because it's not completely compact. If it were the most compact, then it wouldn't be human readable anymore. So if you took the JSON object and just compressed it, you would get something that was smaller, but you couldn't read it. Okay, so it's fairly compact. It's human readable. It's as small as you're going to get and still be human readable. Put it like that. And so the types inside JSON can be combined recursively. When I say the types, the different types of data that you're putting together. So remember that in JSON, we're going to want to represent these different data structures that we have, these objects that we have in Golang. We're going to want to represent them as JSON objects. So they can be combined recursively. So you can have an array of integers, or an array of structures, or a structure with structures inside, or a structure with arrays inside, and integers and strings. So you can combine them all hierarchically, right? A structure with structures inside which have other structures inside, and so on. So you can get arbitrarily complex Golang objects and convert them into JSON. So that's a pretty good advantage. So JSON marshalling. Marshalling, the term marshalling means to, in this case, in JSON marshalling, you're generating JSON, a JSON representation from an object. In our case, a Go object, right? So we've got some object, arbitrarily complex in Go. We want to turn it into something that adheres to JSON format, right? So that's called marshalling, JSON marshalling. So in this example, we're going to start off with our person struct. And here's the general structure. Type struct. It's got a name, address, phone. They're all strings. And this is the structure. So let's say we have an actual person, an object of this particular structure of this type. And this person, P1, it has a particular name, Joe, address A Street, phone 123. We've seen this before. So now we want to take this person, this struct, and we want to turn it into a JSON object. So we call this function JSON marshal, JSON.marshal. And notice that we pass as an argument, we pass P1, the structure, the Golang structure that we want to convert. We pass that as an argument to JSON marshal. And it returns two things. In this case, they're called B. The first thing is B array. I'm calling it, and the next is error. So the error is it's a nil if there's no error. If it converts properly, then this should be a nil. There'll be no error. And what the real what it returns, this B array, is actually going to be a byte array, which it contains the JSON representation. So and remember that JSON is all Unicode. So this byte array is a bunch of runes, basically, an array of them, that is the JSON representation. So what Marshall does, JSON.Marshall does, is it takes a Golang object, returns you a JSON representation. So JSON unmarshalling is going in the opposite direction. What you're trying to do is you take some byte array, which contains a JSON object, and you want to convert that into a Golang object, right, which stores the same information. So going from the last slide, we're again talking about this person struct. So let's say we have already made our BARR, our B array, and that's a person, okay? It's a JSON representation of a person. Now we want to unmarshal it. So we want to take this JSON representation and create a Golang struct which contains the same information. So what we do is we declare that Golang struct. Up there at the top, we say var p2, we'll call it p2, person. So it's a person, but we haven't created it yet. We haven't filled in the name, address, phone yet. So we just have a person, and it's basically empty. Then we call JSON.unmarshal. Now notice there are two arguments we're passing to JSON.unmarshal. First argument is the B array, which is the actual byte array, which contains the JSON object. The second argument is the address of the Go structure that we want the results to be placed into. So address of P2, because remember that this B array, it contains information about a person. We want that to be put into this P2 that we've created that is as of now empty. So when you call it, it just basically unpacks the B array and puts the fields into the attribute values into the appropriate fields of the person structure P2. Now, one thing about this is that one constraint is that this P2, whatever the second argument is to unmarshal, it needs to fit the JSON data, the JSON byte array. When I say fit, I mean the JSON object is going to have a set of attributes and values of those attributes. P2, the second argument, it's got to have the same attributes. So if it's a struct in this case, it's got to have the same, those have to be the field names. So if the JSON object has an attribute called name, then the Golang object P2, it better have a field called name, right? So that's the idea. So it has to fit. But if it does, then what will happen is you call unmarshal, and in the end, P2 will be a struct that contains all the information that was contained in the JSON object. And that error value that's returned by JSON.unmarshal, it's nil if everything works, everything fits. If it doesn't fit, it'll throw an error. Thank you. So files are very commonly used in programs and used to trade data between programs. So we're going to talk about how Golang allows us to access files. We'll give an overview anyway. Now file access, and this is true in all languages, file access is linear access, not random access. So the reason for this is because files, when they were originally defined, they came from, they were actually stored on tapes, right? Physical tapes. And when you access a tape, like you remember, depends on how old you are, but you know, I used to have cassette tapes, right? So, or big old tapes, you've seen them in movies, science fiction movies, big old tapes, right? They turn this physical tape that it's on, and it's linear access, meaning the beginning of the file is at one point in the tape, the end of the file is way over here at the other point of the tape. And so if you want to access it, you got to start, you read one point of the tape, then you got to turn the tape and read the next point. Turn the tape, read the next part, and so on. So it's always linear access. Wherever the turning limits it, right? There's this mechanical operation of physically turning the tape to access the next piece of the file, right? So it's always linear access. If you want to just access something at the beginning, then something at the end, that would waste a lot of time. The beginning's here, then you got to take a lot of time turning to get to the end, right? Instead, you read it linearly. You say, okay, I'm at the beginning and I read everything in that vicinity. You read from the beginning to the end. So that's how file access still is today, even though you don't necessarily have this linear access constraint. I mean, if you look at physical disks, they still have linear access, right? You still have tracks, and you have to go through the whole track. So there's still some linear access in that. But for all we know, a file might be in a random access device. So for instance, a flash memory or something like that, solid state drive, right? That's actually a random access device, but still the way that we access files in programs is as if it's a linear access device. So normally when you access files, you get, in other languages too, you get these set of basic operations that are sort of common for file access. So first one is open. It's getting a handle to start accessing the file. You have to open the file first. Then you always get a read function or some variety of read functions where you can read bytes from the file and read them into, like, say, a byte array. Write, where you write data from a byte array and move that into a file. Close is when you're done, you close the file because you're done reading it or accessing it. And then seek is another thing, a common thing to have. Seek basically moves your read head. So what that means is it's linear access, right? So you read from the beginning to the end, but sometimes you really do need to skip to a certain point, and seek does that. So these are very common functions that you see basically in any language to access files. So there's more than one package in Go that allows you to access files. It has functions in it that allow file access. We'll start with the IOUtil package. IOUtil package has some sort of basic file access functions. Basic, they're easy, they're nice to use if the basics are enough for you. IOUtil is great. So the first function you get there is read file. Now read file, you'll notice that IOUtil.readFile, it takes as an argument the name of the file you want to read. That can be arbitrary, test.txt or whatever you want to call it. And it returns two things: data, basically a byte array, and then an E is the error, right? So it returns two things. An error is only if there's some kind of error reading, but if there isn't an error, its main job is to return this byte array, which is the first thing that it returns. So, and what it does is pretty simple. It just reads the whole file and returns the contents of the whole file into a byte array. And then you can manipulate the byte array. Now, when you use read file, you don't have to do an explicit open or close. You don't have to open the file at the beginning, close it at the end. That's all built into the read file function. So it'll just open the file, read the whole thing, and then close it. So it's nice. One issue with it is that large files can be an issue. So when I say causes a problem, it's not going to cause an error, but files can be gigantic, okay? You can have, if you think about the size of a disk, you can have, the disk can be, a disk can be terabytes, right? I have a terabyte disk in my machine, right? And that's normal, right? So you can have giant sized files. You can have files that really take up most of your memory. Because when you read a file, it takes it off of whatever the storage device is. Let's assume you're using disk for a second, okay? Say I put it on disk, but it could be solid state storage too. It takes it and it reads it into RAM, into its main memory. Now main memory is much more limited. So my disk, I might have, a couple of terabytes, but my RAM, I might only have 8 gigabytes. So I could have a file, an 8 gigabyte long file in my disk that I try to read into main memory. If I read that whole file, I'm using up my whole RAM and my machine will choke, okay? I can't run anything because I've used up all my memory. So when you have large files, read file is, you can't use it, okay? So if your files are small enough so that it doesn't hog up all the memory, then read file is fine. You can just read the whole thing in at once. Now, IOUtil also has a write file function, which is complementary to the read file. And if you look at write file, it takes, it takes 3 arguments. The first argument is the name of the file you're going to write to. The second argument is the byte array, or is a string. And then the third argument is the permission. So remember, write file, it's actually creating a new file. So when I call write file here, I'm going to create a new file called outfile.txt, and it's going to write the data hello world into that file. When it creates that file, it has to give that file permissions, read and write access permissions. So it's using Unix style permission bytes. So 777 means permission for everybody, right? Everybody can do everything. basically. But you can adjust the permissions as you see fit. But those are the arguments to write file. So again, it writes. Now remember, with write file, it's not flexible. You can't append to a file or something. You can't say, oh, let me just add on to the file. Write file, it just creates a file, dumps everything, the whole string or the whole byte array into that file, and then closes the file. So when you're accessing files, we talked about the IOUtil. It gives you some simple functions. But if you want to have a little bit more precise control over file access, then you're probably going to use the OS package. The OS package provides a bunch of functions to access files too. And you can access, you have more control. So with IOUtil, you could read the whole file and write the whole file, and that was about it. With OS package, you can do a little bit more, read a little bit, write a little bit, do different things. So here are some of the functions in there. First, you got os.open, that opens a file. So you pass it the name of the file, and it'll return a file descriptor, a file struct, basically. Call it F, let's say. And it'll return a file descriptor that you can use to access the file. Now, os.close, it closes the file when you're done. os.read reads from a file into a byte array, okay? Now, and it reads to fill the byte array. So you can control how much you read. Unlike with read file and IOUtil, you had to read the whole file. If you only want to read 10 bytes out of it, you can make a byte array of size 10 and pass that to read, and read will fill that byte. So it'll read 10 out. Read however much you need to fill the byte array. And write is a similar thing. You can take a byte array and write that into a file, and it'll just write as much as the byte array is long. So here's an example of file reading using the OS package. So first thing we do is we open the file. So we call os.open, pass it the name of the file, which is completely arbitrary. So we pass it this file name, dt.txt. It opens it, it returns this F, this file handle that we can use to access the file. And an error, if there's an error like the file doesn't exist or something like that, then it'll throw an error, but otherwise it'll return this file handle. Now I'm gonna, for this file I want to read, right? I want to read into some byte array. So let's say I want to read 10 bytes out of this file. So I can make a byte array, B array, colon equal make, I call make, I make it a byte, I give it the type, and I say comma 10. So now I have this byte array, empty byte array. Then I can call f.read. F is the file handle that was returned by open. Call f.read, pass it the byte array as the argument. And it will then fill that byte array with the first 10 bytes out of this file. Now note that if I called it again with that same byte array, it would fill byte array with the next 10, right? Every time the read head actually moves. So I read the first 10. If I read again, it's not going to read the first 10 again. It'll read the next 10 until I close it and it resets the head. This function returns two things: an error if there's an error. So if you're trying to read something and you're out of space, it's empty or something like that, you reach the end of the file, it might throw an error. But otherwise it returns NB, which is the number of bytes that it read. Now sometimes the number of bytes should be equal to the size of the byte array, but it doesn't have to be. You can have what's called a short read. Maybe the byte array is size 10, but there are only 5 bytes left in the file, then you'll only read 5 out. So NB would equal 5 in that case. And then when you're done reading, you just call f.close, and it closes the file and resets the head for the next time. So next example is write. This time using the OS package as well. So first thing we're going to do is we want to write a byte array into a file. So we first create the file in this case, os.create. We could have opened a file. We could have opened an existing file and opened it for append to it. But in this case, we're just going to create, just for an example, we're going to create a new file, call it outfile.txt. And then we get this file handle F that refers to that file. Then we make a byte array actually this is a slice, but we make a slice byte, we're calling it B array, but it's a slice. It has 3 elements in it, 1, 2, and 3. We want to write these. So we call write, f.write. We pass it the byte array, and it just writes those 3 bytes into the file. Now, another thing that we can do, there's another function for writing called write string. That takes an entire string. Instead of a byte array, it takes an explicit string and writes that. So you can call write string hi or something like that, pass it a string, it writes that into the file, and which has to be a Unicode sequence.